Have you ever looked up at the night sky and felt a strange sense of order within the chaos? Those countless points of light aren't scattered randomly. They gather in sweeping spiral galaxies, dance in binary pairs, and follow gravitational rhythms we are only beginning to understand. This feeling that there might be a grand design hidden just beyond our sight is one of the most profound and persistent whispers in the human experience. It's a thought that has captivated philosophers, scientists, and dreamers for millennia. The idea that the universe operates not by chance, but according to a set of deep, elegant, and perhaps even knowable rules. Today, we are going to embark on a journey to listen to that whisper, to pull back the curtain on existence itself, and investigate the astonishing possibility that everything, from the spin of a galaxy to the very structure of an atom, follows a secret cosmic blueprint. This is not just a question for astronomers in observatories. It's a fundamental puzzle that touches the core of our reality. Why do certain mathematical constants appear with uncanny regularity in the most unrelated corners of nature? Why do shapes and symmetries repeat themselves from the microscopic world of a snowflake to the macroscopic structure of the cosmic web? For generations, the greatest minds have worked to crack this code, proposing theories that are as beautiful as they are bizarre. These are not just dry equations on a chalkboard. They are narratives about who we are and what kind of universe we inhabit. They challenge our most basic assumptions about time, space, and matter, suggesting that the world we perceive is merely the surface of something far more intricate and interconnected. We are about to dive into a realm where the solid ground of classical physics gives way to the shimmering possibilities of quantum mechanics, where dimensions may curl up in hidden folds, and information might be the most fundamental currency of reality. So, prepare to have your perspective stretched. We will explore 30 of the most compelling theories that attempt to map the universe's hidden patterns. We will wander from the established pillars of Einstein's relativity to the mind-bending frontiers of string theory and the holographic principle. This is where rigorous science meets profound philosophy, where our quest for knowledge leads us to the very edge of understanding. This journey is about more than just facts and figures. It's an invitation to share in the awe and wonder of discovery, to feel the thrill of peeking at the universe's underlying architecture. Get ready to question everything you thought you knew, because we are about to delve into the deepest mysteries of existence. Our journey begins with perhaps the most fundamental and all-encompassing idea of them all, a theory that takes our hunch of a cosmic blueprint to its ultimate, logical extreme. This is the mathematical universe hypothesis, a concept that suggests the patterns we observe are not just convenient descriptions, but the very substance of reality itself. Imagine for a moment that the universe is not merely described by the language of mathematics, but that it actually is a mathematical structure. In this view, you, me, the stars, and the very fabric of space and time are not just things that can be modeled with numbers and equations. We are the numbers and equations. We are complex patterns within a cosmic computation that is running its course. This profound idea is championed by cosmologists like Max Tegmark, who argues that our physical world is just one of many mathematical structures that exist. Think of mathematics as a vast landscape of all possible logical and consistent systems. Some of these systems are simple, like the geometry of a triangle. Others are unimaginably complex, describing worlds with completely different forces and particles. The mathematical universe hypothesis proposes a staggering conclusion. If a structure can exist mathematically, if its rules are logically consistent, then it must also exist physically in some sense. There is no separate magical, physical substance that gets added. Existence is mathematical existence. This means that a universe where gravity works in reverse, or where time has two dimensions, isn't just a science fiction plot. If its laws can be written down coherently, it is just as real as our own, residing somewhere in a grand, infinite multiverse of mathematical possibilities. What does this mean for our search for patterns? It suggests that the symmetries and constants we discover are not quirks or happy accidents. They are the fundamental, unchangeable parameters of the particular mathematical structure we happen to inhabit. The reason we find the number pi in the ripples of a pond and the orbits of planets is not because nature has a preference for pi, but because our specific cosmic computation has pi built into its core code. This idea transforms our quest from one of discovering the laws of physics to one of discovering which mathematical structure we are a part of. The hidden patterns are not hidden at all. They are the only thing that is truly there, and our perception of a physical world is merely our brain's way of interpreting this underlying mathematical reality. It is a breathtaking perspective that places pure mathematics at the heart of everything, suggesting that the universe is ultimately a cosmos of breathtaking, logical beauty. But if the mathematical universe hypothesis suggests reality is a grand equation, where do we even begin to look for its signature? The answer might be hiding in plain sight, not in abstract numbers, but in the stunningly beautiful and repetitive shapes that nature seems to adore. This brings us to our second theory, an idea that finds a cosmic echo in the very structure of the universe, fractal cosmology. Imagine zooming in on a single flake of snow, observing its intricate, branching arms. Now, picture pulling back, far back, until you see the entire cosmos. Fractal cosmology proposes that the large-scale distribution of galaxies and cosmic voids might not be random, but could instead mirror that same snowflake's complex, self-similar pattern. It's the idea that the universe is structured like a fractal, a geometric shape where the same basic form repeats itself at every scale, from the infinitely small to the astronomically large. The father of this concept is the mathematician Benoit Mandelbrot, who in the 1970s gave a name to these endlessly complex patterns. He observed that many natural forms, coastlines, clouds, ferns, river networks, defy the simple shapes of Euclidean geometry. They are rough, fragmented, and possess a property he called self-similarity. Break off a small piece of a cauliflower, and it looks remarkably like the whole head. Look at a tributary of a great river from above, and its branching shape is a miniature version of the entire watershed. Mandelbrot realized that these objects have a fractional dimension, meaning their complexity increases as you zoom in, seemingly filling more space than a simple line or plane. This was more than a mathematical curiosity. It was a new way of seeing the world's inherent irregularity as a form of deep, hidden order. Astronomers soon began to wonder if the grandest structure of all, the cosmos itself, obeyed this same rule. When we map the universe, we don't find a smooth, evenly distributed soup of galaxies. Instead, we find a vast cosmic web. Long, filamentary chains of galaxies surrounding enormous, empty voids. This web-like structure is hauntingly familiar. It looks like a neural network in a brain, the branching veins of a leaf, or the frothy structure of soap bubbles. Proponents of fractal cosmology argue this is no coincidence. They point to analyses of galaxy surveys that suggest clusters of galaxies group into larger clusters, which in turn form part of even larger superclusters, in a pattern that appears to repeat over a vast range of scales. In this view, there is no one typical size for a structure in the universe. It's patterns within patterns all the way up. This idea gained further intrigue with the detailed study of the cosmic microwave background, the faint afterglow of the Big Bang. Some researchers have claimed to detect fractal-like patterns in the minute temperature fluctuations of this ancient light, hinting that the seeds of the cosmic web were sown with a kind of fractal randomness in the very first moments of existence. However, this is where the theory becomes one of the most contentious in modern cosmology. The central debate hinges on a critical question: does this self-similarity continue forever? The standard model of cosmology, known as the lambda cold dark matter model, posits that on the very largest scales, beyond a certain point, the universe becomes homogeneous and smooth. It's like looking at a forest. Up close, you see the intricate patterns of individual trees, but from a high-flying plane, the forest appears as a uniform green blanket. Most cosmologists believe the universe does the same, that if we could see it on a grand enough scale, the lumpiness of the cosmic web would average out into a smooth, featureless expanse. The controversy is fierce because the answer has profound implications. If the universe is truly fractal at all scales, it would challenge the cosmological principle, a foundational assumption in astronomy which states that the universe is roughly the same in every direction and from every location. A fractal universe would mean there is no average density of matter, no center or edge in the way we typically think, and our place within it might be less typical than we assume. It would suggest a far more complex and hierarchical cosmos than our current models allow. While the majority of evidence currently supports the idea that the universe transitions to smoothness on the largest scales, the allure of fractal cosmology remains powerful. It taps into a deep-seated human intuition that the universe is connected in ways we are only beginning to perceive, offering a vision of cosmic architecture that is both infinitely complex and elegantly simple. But if the universe is a fractal, a pattern echoing across scales, then what is the canvas upon which this pattern is drawn? Our next theory challenges the very nature of that canvas, suggesting that the three-dimensional reality we experience is nothing more than a magnificent illusion. This is the holographic principle, a concept so radical it implies that the universe is actually a projection, a cosmic hologram. To understand how such a breathtaking idea could even arise, we have to journey to the most extreme environments in existence, black holes. The story begins not with holograms, but with a puzzle about information and entropy. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He argued that a black hole, far from being a simple void, must have entropy, a measure of disorder or hidden information. This was controversial because entropy is typically a property of systems with many components, like a gas with trillions of molecules. A black hole, defined only by its mass, spin, and charge, seemed too simple. Yet Bekenstein, advised by John Wheeler, realized that if you were to throw an object with a lot of entropy, like an encyclopedia, into a black hole, that information would seemingly vanish from the universe, violating a key principle of quantum mechanics. Information cannot be destroyed. The solution, Bekenstein suggested, was that the black hole's entropy must increase, and it must be proportional to the surface area of its event horizon, the point of no return. Stephen Hawking later confirmed this by showing black holes radiate heat and have temperature, solidifying the link between gravity, quantum mechanics, and thermodynamics. This was the crucial clue. In everyday life, the amount of information something can contain is proportional to its volume. Your hard drive's capacity depends on its three-dimensional space. But a black hole's entropy, its information content, was tied to its surface area, a two-dimensional boundary. This led Gerard T. Hooft and Leonard Susskind to propose the holographic principle. They argued that perhaps all the information needed to describe everything inside a region of space, every star, every planet, every person, is actually encoded on the surface that surrounds it, like a cosmic DVD. Our reality, in this view, is the three-dimensional movie that this two-dimensional data projects. To make this tangible, think of a hologram on a credit card. That shiny, two-dimensional surface, when hit with light, creates a stunning three-dimensional image that you can look around. The key is that every part of the two-dimensional surface contains information about the whole three-dimensional object. If you were to break the hologram in half, each piece would still contain a faint, blurry version of the entire image, not just half of it. The holographic principle suggests our universe operates in a similar way. The information that defines every particle, every force, and the very fabric of spacetime in our three-dimensional world is stored, pixelated at an unimaginably fine scale, on a distant, two-dimensional surface at the edge of the observable universe. The implications are staggering. It means that the world we see and feel, with its rich depth and solidity, might be a kind of emergent property, a secondary effect. The true, fundamental reality is a vast, complex information field existing in fewer dimensions. This resolves the black hole information paradox. When something falls in, its information isn't lost. It's smeared and encoded onto the event horizon's surface. It also suggests a profound hidden pattern. The universe is fundamentally about information. The laws of physics we study may simply be the rules governing how this cosmic data is translated from a two-dimensional code into the rich, interactive simulation we call reality. It's a theory that blurs the line between the concrete and the conceptual, hinting that the ultimate building blocks of existence are not tiny strings or particles, but bits of information. Yet if the universe is a holographic projection, a compelling question remains. What was the projector, and what set the initial pattern for the cosmic film we now inhabit? This leads us to a cornerstone of modern cosmology, a theory that addresses the very beginning of everything and sets the stage for the universe we see today. We are talking about cosmic inflation, an idea that not only solves profound mysteries about our cosmos, but also opens the door to a reality far grander and more bizarre than we ever imagined. To appreciate the power of inflation, we first need to understand the problems it was designed to solve. For decades after the Big Bang theory was proposed, cosmologists were puzzled by several peculiar features of our universe. The first is the horizon problem. If you look at the cosmic microwave background radiation, the oldest light in the universe coming from opposite sides of the sky, it has exactly the same temperature. This seems logical until you realize that those two regions have never been in contact. In the standard Big Bang model, there hasn't been enough time since the beginning for light, or any influence, to travel between them to equalize their temperature. It's as if two strangers in a massive, crowded room instantly started humming the same tune at the same pitch without ever having spoken. How could such perfect uniformity be established? The second puzzle is the flatness problem. Our universe appears to be incredibly, precisely flat on the largest scales. This isn't flat like a table, but in the geometric sense, where parallel lines stay parallel and the angles of a triangle add up to exactly 180 degrees. For the universe to be this flat after nearly 14 billion years of expansion, its initial conditions at the Big Bang would have had to be fine-tuned to an absurdly delicate degree. Any tiny deviation from perfect flatness in those first moments would have been magnified over time, resulting in a universe that was either dramatically curved and closed in on itself, or a vast, empty, and wide-open expanse. The fact that we observe a balanced, flat universe seems like a cosmic miracle of improbability. In the early 1980s, physicist Alan Guth proposed a brilliant and elegant solution: cosmic inflation. He suggested that a fraction of a second after the Big Bang, around 10 to the power of -36 seconds, the universe was seized by a peculiar, repulsive form of energy inherent to empty space itself. This energy caused the universe to expand at an exponential, faster-than-light rate, doubling in size every tiny fraction of a second. For a fleeting moment, the universe swelled from smaller than a proton to about the size of a grapefruit. This monumental growth spurt, lasting only a tiny fraction of a second, resolves our puzzles with breathtaking simplicity. The horizon problem is solved because the entire observable universe was, before inflation, a tiny, interconnected region that had plenty of time to reach a uniform temperature. Inflation then stretched this tiny, smooth patch into the vast cosmos we see, explaining why opposite horizons look the same. The flatness problem is also resolved. Imagine taking a tiny, wrinkled section of a balloon's surface and inflating it to an enormous size. The inflated section will appear much flatter. In the same way, inflation stretched the fabric of spacetime so dramatically that any initial curvature became smoothed out into the flat geometry we observe. But the true magic of inflation, and the source of the hidden pattern we seek, lies in a quantum mechanical twist. During this ultra-rapid expansion, the universe was not perfectly smooth. On the tiniest quantum scales, there was a constant, fizzing sea of energy fluctuations, particles and antiparticles popping in and out of existence. Inflation acted like a cosmic amplifier, stretching these minuscule quantum ripples to astronomical sizes. A fluctuation that was once smaller than a subatomic particle was suddenly inflated to be larger than a galaxy cluster. These stretched fluctuations became slight variations in the density of matter and energy across the cosmos, and gravity, acting over billions of years, pulled on these denser regions. The slightly denser spots attracted more matter, eventually collapsing under their own weight to form the first galaxies, stars, and everything within them. The grand cosmic web of galaxies, with all its magnificent filaments and voids, is therefore a fossil imprint, a direct map of those quantum mechanical tremors from the universe's first moment of existence. The hidden pattern of the cosmos was literally woven into the fabric of spacetime during its inflationary birth. This leads to the most profound implication of the theory, a concept that truly stretches the imagination. The process of inflation, once started, may be eternal. The repulsive energy driving the expansion could decay in some regions, turning into the hot, dense plasma of a standard Big Bang and creating a bubble universe like our own. But in other regions, inflation could continue forever, constantly spawning new bubble universes in an endless sea of inflating space. This is the inflationary multiverse. Our entire cosmos, with its hundreds of billions of galaxies, may be just one bubble in a boundless, frothing ocean of other universes, each with its own unique set of physical laws and constants. In some, the force of gravity might be stronger, making stars burn out quickly. In others, the nuclear forces might be too weak for atoms to ever form. The hidden pattern we observe in our universe, the specific values of its constants that allow for our existence, may not be a fundamental law, but simply a local ordinance within our particular cosmic bubble. This idea transforms our perspective, suggesting that the search for a single, elegant theory of everything might be misguided. Instead, we may live in a vast and varied multiverse where every possible reality exists somewhere, and our universe's patterns are just one possible outcome in an infinite landscape of cosmic potential. This idea of a multiverse, where our universe is just one bubble in an endless cosmic foam, brings us face to face with one of the most profound and debated concepts in all of science and philosophy, the anthropic principle. It directly tackles a mystery that has troubled physicists for decades, a pattern so striking it seems to whisper of design. Why is the universe so hospitable to life? The fundamental constants of nature, the strength of gravity, the mass of an electron, the force that binds atomic nuclei appear to be exquisitely fine-tuned. If any one of these values were even slightly different, the cosmos as we know it would be impossible. A little stronger gravitational force, and the universe would have collapsed back on itself moments after the Big Bang. A little weaker nuclear force, and stars would never have ignited. The list of these cosmic coincidences is long and deeply unsettling for anyone who believes the universe is a product of blind chance. The anthropic principle is an attempt to make sense of this apparent fine-tuning, and it does so by shifting the focus from the universe itself to us, the observers. We must distinguish between two main interpretations of this principle, as they lead to dramatically different conclusions. First, there is the weak anthropic principle. This is the less controversial version, essentially a statement of a selection effect. It says that we should not be surprised to find ourselves in a universe capable of supporting life, because if the universe were not capable of supporting life, we would not be here to observe it. It's a logical truism. Imagine a puddle waking up one morning and marveling at how perfectly the hole it resides in fits its shape. The puddle might conclude that the hole was designed specifically for it. But the reality is simply that water fills the available cavity. In the same way, the weak anthropic principle suggests we are simply the water that has filled the cosmic hole that happens to be suitable for us. We only observe this particular set of constants because it's the only set that allows for observers to exist. This view doesn't require any special purpose or design. It's just a consequence of our own existence. It connects beautifully to the inflationary multiverse idea. In a vast landscape of universes with different physical laws, we naturally find ourselves in one of the rare, life-permitting bubbles. The pattern of fine-tuning isn't a pattern at all, but a statistical inevitability given an infinite number of trials. Then there is the strong anthropic principle. This is where the waters get much deeper and more controversial. This version asserts that the universe must have properties that allow life to develop within it at some stage in its history. The word "must" is crucial here. It implies a form of teleology, that the universe is in some sense directed towards the goal of producing conscious life. Proponents of this view argue that the incredible precision of the constants points to something more than just luck, even a multiversal luck. They suggest that perhaps the laws of physics are not arbitrary, but are somehow constrained by the necessity of producing observers. This line of thinking resonates with certain interpretations of quantum mechanics, where the act of observation seems to play a fundamental role in determining reality. It also opens the door to philosophical and even theological interpretations, where the fine-tuning is evidence of a cosmic designer or a universe that is inherently conscious. Critics, however, argue that the strong anthropic principle is not a scientific explanation at all, but a tautology that explains nothing. It simply replaces one mystery, why the constants are what they are, with another, why the universe must produce life. The debate between these two interpretations forces us to confront the very nature of scientific inquiry. Is our universe just one random ticket in a cosmic lottery? Or is there a deeper reason for its life-friendly properties? The fine-tuning argument remains one of the most powerful pointers toward a multiverse, as it offers a naturalistic explanation for what otherwise looks like a miracle. Yet, it also highlights the unique position we hold. Our ability to ponder these questions, to measure the constants, and to be baffled by their values, is itself a product of those very constants. This self-referential loop is at the heart of the anthropic reasoning. It suggests that the search for the universe's hidden patterns is not a detached, objective exercise. We are not separate from the cosmos we are trying to understand. We are an emergent property of its laws. The patterns we discern, from the mathematical elegance of inflation to the apparent fine-tuning for life, are inextricably linked to the fact that we are here, in this particular universe, capable of the act of observation itself. Yet if the anthropic principle offers a reason for our universe's laws, it leaves a deeper mystery untouched. What is the ultimate, unified origin of those laws themselves? For decades, physics has been haunted by a fundamental schism. On one hand, we have Einstein's general relativity, which masterfully describes the force of gravity as the curvature of spacetime on immense cosmic scales. On the other, we have quantum mechanics, which with astonishing precision governs the bizarre world of atoms and subatomic particles. The problem is that these two pillars of modern physics are fundamentally incompatible. Their equations break down when pushed to extremes, like the center of a black hole or the first moment of the Big Bang. This conflict points to a missing piece, a deeper layer of reality where a single, elegant framework unites the very large and the very small. This is the quest for a theory of everything, And one of the most ambitious, mathematically beautiful, and perplexing candidates is string theory. String theory begins with a radical reimagining of the fundamental building blocks of nature. For centuries, we have thought of particles as infinitesimal points, like zero-dimensional dots. But string theory proposes that at the heart of every electron, every quark, every particle that makes up the universe, there is not a point, but a tiny vibrating loop or filament of energy, a string. These strings are unimaginably small, on the order of the Planck length, which is about a millionth of a billionth of a billionth of a billionth of a centimeter. Far too small to be detected by any instrument we can currently conceive. The crucial insight is that the differences between particles are not due to them being made of different stuff, but rather a consequence of how these identical strings vibrate. Much like a single violin string can produce different notes depending on how it is plucked, a G, a D, an A. The distinct vibrational patterns of these fundamental strings manifest as the different particles we observe. One resonant frequency might correspond to an electron, another to a photon, another to a quark. In this view, the entire universe is a cosmic symphony, and the hidden pattern underlying all matter and force is simply the music of these vibrating strings. This elegant idea, however, comes with a monumental requirement that pushes our understanding of reality to its limits. For the mathematics of string theory to be consistent, to avoid nonsensical answers like probabilities greater than 100%, the equations demand that spacetime must have more than the 3 spatial dimensions and 1 time dimension we experience. The earliest versions required 26 dimensions, but the most developed form, superstring theory, requires 10 dimensions, 9 of space and 1 of time. So where are these extra dimensions? The theory proposes they are compactified or curled up into a shape so incredibly tiny that they are hidden from our perception. A classic analogy is a garden hose. From a distance, the hose appears to be a simple one-dimensional line. But if you could shrink down to the size of an ant and crawl onto it, you would discover it has a second dimension, curled around its circumference. In the same way, at every point in our 3-dimensional space, string theory suggests there are 6 additional spatial dimensions curled into a complex, microscopic geometric shape called a Calabi-Yau manifold. The specific way these dimensions are folded determines the possible vibrational modes of the strings, which in turn dictates the laws of physics in our observable universe, from the number of particle families to the strength of the forces. The pattern of the cosmos is thus literally shaped by the geometry of these hidden, compactified dimensions. The promise of this framework is breathtaking. String theory doesn't just aim to describe particles, it naturally incorporates gravity. The particular vibrational mode of a closed string corresponds to a particle called the graviton, the hypothetical carrier of the gravitational force. This offers the first credible path to uniting gravity with quantum mechanics, weaving them both into a single, coherent tapestry. For this reason, string theory is often heralded as the leading candidate for a theory of everything, a single set of equations capable of describing every force and particle in nature. It suggests a universe of profound unity, where the dizzying diversity we see is merely different expressions of one fundamental object. Yet, for all its mathematical beauty and promise, string theory faces a significant and perhaps existential challenge: a complete lack of experimental evidence. The energy levels required to directly probe the scale of strings or to uncurl those compactified dimensions are far beyond the reach of any particle accelerator we could ever build, being trillions of times more powerful than the Large Hadron Collider. This has led to a major criticism. If a theory cannot be tested, can it truly be considered science? Furthermore, instead of providing a unique prediction of our universe, string theory appears to offer a staggering multitude of possibilities, perhaps 10 to the power of 500 different vacuum states or ways for the extra dimensions to curl up. Each configuration would yield a different set of physical laws, leading to a different universe. This landscape, problem means that string theory may not predict a single, unique universe, but rather a vast multiverse, potentially aligning with the ideas of eternal inflation and the anthropic principle. For some, this is a profound feature, explaining our universe's fine-tuning. For others, it's a fatal flaw, rendering the theory untestable and devoid of predictive power. The hidden patterns of string theory, for now, remain locked within the equations, a beautiful and compelling map of a reality we cannot yet touch, leaving us to wonder if we are on the verge of a final theory or merely captivated by an intricate mathematical dream. But if the laws of physics are a kind of cosmic software, a question emerges that pushes the boundaries of science and philosophy alike. Could our entire reality be the product of a deliberate creation, a simulation running on a computer of unimaginable power? This brings us to one of the most provocative and widely discussed ideas about the nature of existence, the simulation hypothesis. This is not merely a plot from a science fiction movie. It is a serious, if speculative, argument that has garnered attention from philosophers, technologists, and even some physicists. The core premise is startlingly simple. If a civilization could ever reach a level of technological maturity sufficient to create incredibly detailed, conscious simulations of its own history or of entirely fictional universes, then the number of simulated realities would vastly outnumber the one base, original reality. If that is the case, the statistical probability is that we are not the original civilization, but one of the countless simulations. The modern argument was famously articulated by the philosopher Nick Bostrom. He breaks it down into a trilemma, meaning one of three propositions must be true. First, it's possible that almost all civilizations like ours go extinct before reaching a post-human stage capable of running such simulations. Second, it's possible that any civilization that does reach that stage would have absolutely no interest in running vast numbers of simulations of their own past. If either of those first two are true, then we are almost certainly living in the original, base reality. But the third proposition is the one that captures the imagination. If a significant number of advanced civilizations do reach that technological stage, and they have even a modest interest in running ancestral simulations for research, entertainment, or archival purposes, then the number of simulated minds would be astronomically greater than the number of biological ones. From a sheer numbers game, you would have to conclude that you are more likely to be one of those simulated beings. It's a cosmic version of the lottery. If there are 1 billion simulated tickets for every one real ticket, the odds are overwhelmingly against you holding the original. So, if we are living in a simulation, what might be the telltale signs, the hidden patterns in the code? Proponents of the hypothesis point to certain features of our universe that bear a curious resemblance to the shortcuts and limitations a programmer might use to manage computational resources. One of the most compelling clues lies in the fundamental nature of reality itself. Quantum mechanics has shown us that at the smallest scales, the universe is not continuous and smooth, but granular and discrete. Energy comes in packets called quanta. Space and time themselves may also have a fundamental graininess. The Planck length and Planck time are theorized to be the smallest possible units of distance and duration, beyond which the concepts of length and time lose their meaning. This is remarkably similar to the pixels on a screen or the frame rate of a video game. The simulation isn't infinitely detailed, it has a resolution. The laws of physics, with their elegant, mathematical precision, could be seen as the underlying algorithms that govern the simulation's engine, ensuring consistency and predictability without requiring infinite processing power. These potential glitches in the matrix could manifest in other ways. Have you ever experienced a strange coincidence, a déjà vu, or witnessed a particle in a quantum experiment behaving in a way that seems to defy logic until it is observed? Some suggest these could be interpreted as minor processing errors or background optimization routines. Furthermore, the very speed limit of our universe, the speed of light, could be seen as a data processing constraint, the maximum rate at which information can be transmitted between different parts of the simulation to maintain causal consistency. Even the search for a unified theory of physics, a single elegant equation that describes everything, fits the narrative. A sophisticated simulation would likely be built on a parsimonious, efficient codebase. The fact that we keep finding deeper layers of mathematical order, from general relativity to quantum field theory, suggests we are reverse engineering the source code of the simulation, discovering the elegant algorithms the programmers used to construct our reality. Of course, this idea is met with significant skepticism. Many argue it is an untestable, and therefore unscientific, hypothesis. If the simulation is perfect enough to create conscious beings who can ponder their own existence, then any glitch we might find could simply be explained as a feature of the base reality's laws, not proof of a simulation. The hypothesis also raises profound philosophical questions about consciousness. Could a simulated mind ever be truly conscious? Or would it just be a sophisticated zombie going through the motions? And if we one day create such simulations ourselves, what ethical responsibilities would we have towards the beings within them? The simulation hypothesis ultimately serves as a powerful mirror, reflecting our own technological ambitions and our deepening understanding of information as a fundamental component of the cosmos. It suggests that the ultimate hidden pattern might not be a geometric shape or a vibrating string, but a grand computational algorithm, and that our quest for knowledge is, in a very literal sense, a journey to read the source code of the universe. Building on the idea of a universe governed by elegant, mathematical rules, we encounter a concept that is arguably the most beautiful driver of physical law itself: symmetry. This isn't just the simple symmetry of a butterfly's wings or a snowflake's design. In physics, symmetry refers to a deeper principle that the laws of nature remain unchanged under a specific transformation. Think of a perfect circle. You can rotate it by any angle and it looks exactly the same. The circle is symmetric under rotation. This simple idea, when applied to the abstract fabric of reality, becomes an incredibly powerful engine for discovery. Physicists have found that demanding certain symmetries in their equations actually forces the existence of the fundamental forces we observe. The requirement for a particular kind of symmetry, known as gauge symmetry, is what gave us the equations for the electromagnetic, weak, and strong nuclear forces. It's as if the universe's deep-seated preference for balance and order is what writes the rules of interaction, dictating that for every action there must be an equal and opposite reaction, but on a cosmic scale. However, there is a haunting asymmetry in our current best model of particle physics, the Standard Model. The particles that make up the cosmic catalog are divided into two distinct families that seem to live by different rules. On one side, we have the fermions, the particles of matter, like electrons and quarks. They are the stubborn individualists of the particle world, obeying the Pauli exclusion principle, which means no two fermions can occupy the same quantum state. This is why matter is solid. It's why atoms have structure and you don't just fall through your chair. On the other side, we have the bosons, the force carriers like photons and gluons. They are the sociable mediators, able to pile on top of each other in unlimited numbers, which is how they transmit forces. For decades, this divide seemed absolute, a fundamental schism in the nature of reality. But what if this was just an illusion? What if there was a deeper, hidden symmetry connecting these two seemingly separate worlds? This is the breathtaking promise of supersymmetry, often called SUSY. It proposes a radical new kind of symmetry, one that transcends the matter-force divide. SUSY suggests that for every known fermion, there should be a supersymmetric boson partner, and for every known boson, a supersymmetric fermion partner. These hypothetical particles are whimsically named. The electron's partner would be the selectron, the quark's partner the squark, and the photon's partner the photino. This isn't just a whimsical doubling of the particle zoo. It's a profound mathematical extension that would weave matter and force into a single, cohesive tapestry. If Sussy is true, then the universe possesses a symmetry more profound than any we have yet discovered. A hidden pattern that treats the building blocks of you and me and the forces that hold us together as two sides of the same cosmic coin. The motivation for such an elegant idea is driven by one of the most nagging problems in fundamental physics, the hierarchy problem. This problem boils down to a question of inexplicable balance. The mass of the Higgs boson, the particle that gives all other particles their mass, is incredibly fine-tuned. According to quantum theory, the Higgs mass should be pulled up to an enormously high value, near the Planck scale, by its interactions with all the other particles. This would make the Higgs astronomically heavier than it actually is, and would throw off the entire delicate balance of the Standard Model, making atoms unstable and life impossible. To get the measured, relatively low mass of the Higgs, the theoretical contributions from other particles would have to cancel each other out with an accuracy of 1 part in a million billion. This seems like an unbelievable cosmic coincidence. Supersymmetry offers a graceful solution. In a supersymmetric universe, every Standard Model particle has a superpartner. The key is that the quantum contributions of a particle and its superpartner to the Higgs mass are equal in magnitude but opposite in sign. They cancel each other out perfectly and naturally, solving the hierarchy problem without any need for miraculous fine-tuning. The stability of our universe would no longer be a mystery, but a direct consequence of this deep, underlying symmetry. Furthermore, Sussy provides a compelling candidate for the mysterious dark matter that makes up about 85% of the matter in the cosmos. The lightest supersymmetric particle, often thought to be a neutralino, would be stable and would not interact with light, making it a perfect fit for the profile of dark matter. This would solve two of the biggest puzzles in cosmology with one elegant theoretical framework. For these reasons, many physicists were supremely confident that the Large Hadron Collider would discover evidence for supersymmetry soon after it turned on. The stage was set for a revolution. Yet, as the collider collected more and more data, the predicted superpartners failed to appear. No selectrons, no squarks, no photinos. This has been a profound disappointment for the theory. The particles are either much heavier than anticipated, meaning the natural cancellation for the Higgs mass is not as perfect as hoped, or nature has chosen a different path altogether. The elusiveness of Sussy forces us to confront a difficult question. Is the universe's hidden pattern simply more subtle than we imagined? Perhaps supersymmetry is not broken in the simple way we expected, or maybe it manifests at energy scales we cannot yet probe. Some theorists hold onto the hope that the next generation of colliders will find the evidence. Others see it as a sign that while the mathematics of Sussy is beautiful, it may not be a feature of our particular reality. This tension between mathematical elegance and experimental fact lies at the heart of modern physics. It reminds us that the universe is under no obligation to conform to our aesthetic preferences for neat and tidy solutions. The search for supersymmetry continues, a testament to our enduring belief that beneath the apparent complexity of the cosmos lies a simpler, more symmetric, and profoundly beautiful order. While the idea of a single, linear Big Bang leading to an eternal expansion is the dominant picture, it is not the only compelling narrative for our cosmos. Another profound possibility suggests that the universe is engaged in an endless, rhythmic dance of birth, death, and rebirth. This is the cyclic model, a vision of the cosmos not as a one-time event, but as a phoenix, perpetually rising from its own ashes in cycles that stretch into the infinite past and future. The hidden pattern here is not a static blueprint, but a cosmic heartbeat, a grand, eternal return where the universe's history might repeat itself in broad, sweeping strokes. One of the most developed versions of this idea is the ekpyrotic universe model, a name derived from the Greek word for conflagration, or out of fire. This theory is deeply intertwined with the concepts of string theory and extra dimensions. It proposes that our observable universe is a three-dimensional membrane, or brane, existing within a higher dimensional space. Nearby, there is another such brane, a parallel universe separated from us by a tiny gap in an extra dimension. The Big Bang in this scenario was not the beginning of time and space, but merely a violent, transformative event in an already existing cosmos. It was the result of a collision between our brane and the parallel one. This collision released an immense amount of energy, heating our brane to an incredible temperature and setting off the period of expansion and cooling we now call the Big Bang. After the collision, the two branes bounce apart, and the universe we know begins to evolve, with galaxies, stars, and planets forming. But the story doesn't end there. Over trillions of years, as the universe continues to expand, the dark energy that now drives its acceleration might weaken or reverse. The branes, drawn together by a subtle force across the higher dimensional bulk, would begin to move toward each other once more, setting the stage for the next cataclysmic collision and the birth of a new cosmic cycle. In this view, the Big Bang is not a unique beginning, but a regular occurrence in an eternal sequence. This concept of a cyclic universe offers an elegant alternative to the singularity problem that plagues the standard Big Bang model. The initial moment of the Big Bang is a point of infinite density and temperature where the laws of physics as we know them break down completely. The cyclic model avoids this by replacing the singularity with a well-defined, high-energy collision between two branes. The universe is never squeezed into an infinitely small point. It is simply reset through a tremendous but finite impact. Furthermore, the ekpyrotic model provides a natural explanation for the uniformity we see in the cosmic microwave background. As the two branes move toward each other in the pre-collision phase, quantum fluctuations along their surfaces get stretched and smoothed out, creating the seeds for the large-scale structure of the next cycle without requiring a separate period of inflation. It's a different mechanism, but with a similar outcome: a smooth, flat universe primed for galaxy formation. However, this idea of an eternal return immediately confronts a fundamental feature of our reality, the arrow of time, as defined by the second law of thermodynamics. This law states that entropy, a measure of disorder, always increases in a closed system. It's why a hot cup of coffee cools down in a cold room, but never spontaneously heats up. It's why you can scramble an egg but never unscramble it. The universe as a whole appears to be on a one-way trip from a state of low entropy at the Big Bang to a state of maximum entropy, often called the heat death, where all energy is evenly distributed and no more work can be done. If the universe is cyclic, how does it reset its entropy? How does a universe heading toward a featureless heat death manage to contract into a hot, dense, low-entropy state to begin a new cycle? This seems to violate the most fundamental arrow we have. Proponents of cyclic models propose a fascinating resolution. They suggest that during the contraction phase, something extraordinary happens. As the universe collapses, the enormous gravitational pull of black holes, which have been accumulating over the cycle, begins to dominate. These black holes eventually merge and evaporate through Hawking radiation, but in the final moments of the contraction, this process might effectively erase the universe's history. All the complex structures, the galaxies, the stars, the planets, every record of what happened are utterly scrambled and destroyed. The information they contained is lost, and the universe is returned to a simple, homogeneous, low-entropy state, ready for the next bounce. In this way, each cycle is not an exact replay of the last. The specific details, the particular arrangement of galaxies and the stories of civilizations, are wiped clean. The hidden pattern is not in the fine details, but in the overarching rhythm itself, the repetition of the laws of physics, the formation of large-scale structure, and the inevitable evolution toward complexity, all of which are imprinted anew with each collision. The universe forgets its past lives, remembering only the fundamental rules of its existence, allowing the cosmic dance to begin again forever. This idea of a cosmic cycle, where the universe forgets its past with every rebirth, presents a stark contrast to another profound mystery where connections seem to defy the very idea of distance and separation. This brings us to a phenomenon so strange that it troubled the great Albert Einstein himself, a cornerstone of quantum mechanics that suggests a hidden pattern of deep, instantaneous connection woven into the fabric of reality. We are talking about quantum entanglement, a concept that forces us to question the most basic assumptions about how the universe operates. To grasp why entanglement is so revolutionary, we first need to understand the classical view of the world it shatters. In our everyday experience, objects are separate and localized. If you have two identical coins and you mail one to a friend on the other side of the world, the coin you keep remains independent. Flipping your coin here tells you nothing about the state of the coin far away. Each is its own distinct entity. This principle of local realism, that objects have definite properties and can only be influenced by their immediate surroundings, was the bedrock of physics for centuries. But the quantum world operates by a completely different set of rules. At the subatomic level, particles like electrons or photons can become inextricably linked or entangled. This means that the quantum properties of these particles, such as their spin or polarization, are not defined individually but are described by a single, shared quantum state. They become a unified system, even if they are later separated by vast cosmic distances. The true magic, and the source of the spookiness, is what happens when you measure one of these entangled particles. Imagine you have a pair of entangled electrons. Quantum mechanics tells us that before measurement, neither electron has a definite spin. They exist in a fuzzy superposition of both possible states, say, up and down simultaneously. But the moment you measure the spin of the first electron and find it to be up, the state of the second electron is determined instantaneously. It will always be found to be down, no matter how far apart they are. This connection appears to happen faster than light, a clear violation of the local realism that Einstein held dear. He famously derided this as spooky action at a distance, believing it was evidence that quantum mechanics was an incomplete theory. He argued that there must be some hidden variables, unknown factors predetermined at the moment of entanglement, that would explain the correlation without any need for faster-than-light communication. For decades, this remained a philosophical debate. But in the 1960s, physicist John Bell devised an ingenious mathematical theorem that could experimentally test Einstein's hidden variables against the standard quantum view. Bell's inequality set a limit on the strength of correlations between particles if local hidden variables were true. If experiments showed correlations stronger than this limit, then local realism would be violated, and quantum mechanics would be proven correct in its spookiness. Over the years, a series of increasingly sophisticated experiments, most famously by Elaine Aspect and others, have been conducted. The results have been decisive and breathtaking. The quantum correlations violate Bell's inequality. The particles are indeed connected in a way that cannot be explained by any local, hidden information. When you measure one entangled particle, its partner really does respond instantly, as if space and distance between them simply don't matter. This confirmation of non-locality has staggering implications for our understanding of reality. It suggests that at the most fundamental level, the universe is not a collection of separate, independent objects, but a deeply interconnected web. The illusion of separation might be just that, an illusion emerging from our macroscopic perspective. This interconnectedness hints at a hidden pattern where the universe is fundamentally holistic. Some interpretations of quantum mechanics, like the pilot wave theory, attempt to restore a form of determinism, but at the cost of introducing a non-local guiding wave. Others, like the many worlds interpretation, suggest that the correlation is explained by the fact that the two measurements become linked across branching parallel universes. But perhaps the most profound implication is for the nature of spacetime itself. The phenomenon of entanglement challenges the very idea that space is a primary, fundamental stage. It's possible that space is not the arena in which things happen, but rather an emergent property that arises from a vast, underlying network of quantum entanglement. In this view, the connectivity between things might be more basic than the space that appears to separate them. The spooky action at a distance might not be an anomaly but a clue, a glimpse into the fundamental code of the cosmos where everything is linked in a pattern of relationships that transcends our conventional understanding of location and causality. Yet this intricate web of instantaneous connection, as baffling as it is, operates within a universe where motion and change appear to follow a different, almost purposeful kind of logic. There is another hidden pattern, one that is not about spooky connections but about a profound and universal economy of motion. This is the principle of least action, an idea so powerful and elegant that it seems to reveal a deep-seated preference for efficiency written into the very laws of physics. The principle suggests that when anything in the universe moves, a light ray bending through a lens, a planet orbiting a star, or a ball rolling down a hill, it doesn't just follow the push and pull of forces as described by Newton. Instead, it behaves as if it is, choosing the single, optimal path from a vast menu of possibilities, the one that minimizes or, more accurately, extremizes a specific mathematical quantity known as the action. To grasp this abstract idea, let's consider a simple, everyday scenario. Imagine a lifeguard on a beach who needs to rescue a swimmer in distress. The swimmer is not directly straight out from the shore, but somewhat down the beach. The lifeguard could run in a straight line directly into the water, and then swim straight to the swimmer. But that would be slow, because running on sand is much faster than swimming in water. A smarter path would be to run a longer distance on the fast sand, and then swim a shorter distance in the slow water. The path that gets the lifeguard to the swimmer in the least amount of time is not a straight line, but a bent one, with a specific angle at the point where they enter the water. This is an example of a least time path, and it's directly analogous to how light behaves when it refracts or bends as it passes from air into water. Light doesn't take the shortest distance, it takes the path of least time. This observation, made by the French mathematician Pierre de Fermat in the 17th century, was an early hint that nature operates on a principle of optimization. The full principle of least action was developed a century later by thinkers like Pierre-Louis Maupertuis and Leonhard Euler, and later perfected by Joseph Louis Lagrange and William Rowan Hamilton. They defined action not just as time, but as a more general quantity that combines the energy of a system with its path over time. For a moving object, the action is roughly the difference between its kinetic energy of motion, and its potential energy, stored energy averaged over the entire journey. The stunning revelation was that the actual path any object takes between 2 points is the one for which this total action is stationary, meaning it is either a minimum, a maximum, or a saddle point, though it's most often a minimum. Think of a ball rolling from a high point to a low point across a warped landscape. It could take any number of winding routes, but the path it actually takes is the one that perfectly balances its speed and its descent, resulting in the least possible total action. It's as if the ball evaluates every conceivable route in advance and selects the most economical one. This is far more than a convenient trick for solving physics problems. It is a fundamental reframing of how we understand causality in the universe. Newton's laws are differential. They tell you the force acting on an object at an instant, and from that you can calculate its acceleration, then its velocity, and finally its position, step by step into the future. It's a local, moment-to-moment description. The principle of least action, in contrast, is global and holistic. It doesn't care about the forces at each point along the way. It considers the entire trajectory from start to finish all at once. It says that the entire history of the object's motion is determined by a single, overarching optimizing principle. This shift in perspective is monumental. It suggests that the universe isn't just a series of cause and effect events, but rather that the entire path of any process is somehow selected in one fell swoop based on a grand, cosmic criterion of optimality. The true power of this principle is revealed by its universality. It is not confined to the world of baseballs and planets. This same variational principle became the very foundation for all of modern physics. When James Clerk Maxwell unified electricity and magnetism into electromagnetism, his famous equations can be derived from a principle of least action. When Einstein revolutionized our understanding of gravity with general relativity, the equations that describe the curvature of spacetime themselves emerge from demanding that the action for gravity be stationary. And in the bizarre world of quantum mechanics, the principle takes on a truly wondrous form. Richard Feynman showed that a quantum particle doesn't take just one path. It effectively takes every possible path simultaneously. However, for most of those paths, the associated actions interfere with each other and cancel out. The path that we actually observe, the classical, Newtonian path, is the one where the action is stationary, because the quantum waves for paths near it reinforce each other. So, at the quantum level, the principle of least action is not a strict rule, but a statistical emergence from the underlying fuzzy probability waves. The universe appears to be an optimization problem at its very core, with the laws of physics being the mathematical expression of this deep-seated tendency toward efficiency. This hidden pattern of economy hints at a cosmos that is not just orderly, but in some profound sense, intelligently designed for simplicity and elegance. But this cosmic preference for economy and elegance, as universal as it seems, may not be the final word. As we map the universe on the grandest scales, astronomers have stumbled upon a mystery so profound it suggests our entire cosmic neighborhood might be caught in a vast, unseen current, flowing towards something we cannot see. This is the enigma of dark flow, a discovery that points to a hidden pattern of motion which, if confirmed, would force us to rewrite our most basic assumptions about the cosmos. The story begins with our most detailed map of the infant universe, the cosmic microwave background radiation. This afterglow of the Big Bang is remarkably uniform, but it contains tiny temperature fluctuations that are the blueprints for all future structure. According to the standard model of cosmology, these primordial ripples should have set everything in the universe moving in random, chaotic directions. Over billions of years, the gravitational pull of massive structures like galaxy clusters should have created a complex web of motions. But when you average it all out on the very largest scales, there should be no preferred direction for the universe's overall drift. The cosmos, in essence, should be going nowhere in particular. This expectation is a cornerstone of the cosmological principle, which states that the universe is homogeneous and isotropic, meaning it looks roughly the same in every direction and from every location. However, when a team of scientists led by Alexander Kashlinsky analyzed the motion of massive galaxy clusters using data from NASA Wilkinson Microwave Anisotropy Probe, or WMAP, they found something astonishingly different. They weren't looking at the galaxies themselves, but at a subtle effect these clusters have on the cosmic microwave background radiation. This technique, known as the kinetic Sunyaev-Zeldovich effect, works by measuring how the hot gas within a galaxy cluster scatters the ancient photons of the microwave background. The motion of the cluster towards or away from us imprints a tiny, specific signature on this scattered light, a kind of Doppler shift that allows scientists to measure the cluster's velocity with incredible precision. What Kashlinsky's team found was that hundreds of clusters, stretching out billions of light years from Earth, were all streaming in the same direction at velocities of nearly 1,000 kilometers per second. This wasn't a small, local motion. It was a coherent flow on a scale that defied explanation by any known gravitational source within the observable universe. They named this phenomenon dark flow, by analogy with dark matter and dark energy, because its cause remains completely invisible to us. The implications of this discovery are staggering. If this flow is real, what could possibly be pulling on so much matter with such immense force? The gravitational pull required would have to come from a structure of unimaginable mass, far beyond the scale of any supercluster we know. The most mind-bending possibility is that the source of this gravitational tug lies beyond the boundary of our observable universe. Remember, the observable universe is just the part of the cosmos from which light has had time to reach us since the Big Bang, a sphere about 93 billion light-years in diameter. But the entire universe could be vastly larger, perhaps infinite. The dark flow could be evidence that there are enormous mass concentrations, other universes, or remnants from a time before our Big Bang, residing in this unseen territory, whose gravity is somehow reaching across the cosmic horizon and influencing us. In a multiverse scenario, our bubble universe might be drifting relative to its neighbors, and we are simply feeling the gravitational tide from a neighboring cosmic island. Naturally, a claim this extraordinary has been met with intense scrutiny and controversy. Other teams analyzing data from more recent missions, like the Planck satellite, have questioned the statistical significance of the finding, suggesting it could be an artifact of incomplete data or systematic errors in the measurement technique. The debate is highly technical, revolving around the meticulous subtraction of foreground signals from our own galaxy and the precise calibration of the instruments. Proponents of dark flow argue that their methods are sound and that the signal persists even in the latest data sets. They point out that if the flow is caused by something outside our horizon, its influence would have been imprinted on our universe in its earliest moments, during the inflationary epoch, and thus would be a fossil relic of a reality that predates or exists alongside our own. This idea challenges not only the cosmological principle, but also our understanding of what happened at the very beginning. It hints that the Big Bang may not have been a perfectly uniform event, and that the seeds of large-scale structure might have origins far more exotic than simple quantum fluctuations. Whether dark flow is ultimately confirmed or refuted by future observations, its investigation highlights a crucial truth in our quest to understand the cosmos. The largest patterns may be the most difficult to see, and the most fundamental laws we hold dear may have exceptions on scales we are only beginning to probe. It forces us to consider that the uniformity we perceive might be a local phenomenon, and that our universe could be part of a grander, more dynamic structure, whose full shape and motion remain hidden in the darkness beyond our view. But if the universe is ultimately headed for a cold, featureless heat death governed by the relentless rise of entropy, we encounter a philosophical puzzle so strange, it seems to undermine the very act of thinking about it. This is the Boltzmann brain paradox, a thought experiment that takes the laws of thermodynamics to their most absurd and unsettling conclusion. It's a concept that forces us to question not just the fate of the cosmos, but the reliability of our own memories and senses. The paradox is named for the 19th century physicist Ludwig Boltzmann, who pioneered our understanding of entropy. He helped us see that the universe's journey from order to disorder is a matter of probability, not an absolute law. A state of low entropy, like all the air molecules in a room gathering in one corner, is not impossible. It is just incredibly, mind-bogglingly unlikely. But in a universe that is infinite in size or eternal in duration, even the most improbable events are not just possible. They are inevitable, given enough time and space. To understand why this leads to such a bizarre result, imagine a box containing a gas. In its most probable high-entropy state, the gas molecules are evenly distributed throughout the box. This is equilibrium, but every once in a great while, just by random chance, the molecules will momentarily arrange themselves into a more ordered state. like briefly forming a recognizable shape. Now, scale this idea up to the entire cosmos. In a universe that has existed for trillions upon trillions of years and has reached a near-total state of equilibrium, a cold, dark, and uniform emptiness, a random fluctuation in the quantum field could, by sheer accident, cause a bunch of particles to assemble into a fully formed, self-aware human brain. This brain would pop into existence complete with fabricated memories of a past life, a sense of being in a body, and the illusion of being surrounded by a world. It would think it was a person named Ludwig, sitting in a cafe in Vienna, pondering the laws of physics, when in reality, it is just a momentary flicker of order in an eternal sea of chaos. This phantom observer is what we call a Boltzmann brain. The paradox arises when we apply this logic to our own situation. Our current universe is in a state of remarkably low entropy. We have galaxies, stars, planets, and life, all examples of exquisite order. The standard scientific story is that this order evolved over billions of years from the low entropy conditions of the Big Bang. But from the perspective of probability, which is more likely, that an entire 13.8 billion-year-old universe with hundreds of billions of galaxies would spontaneously form from a random fluctuation. Or that a single, self-aware brain with the false memory of such a universe would momentarily flicker into existence. The answer, staggeringly, is the single brain. The odds of an entire ordered cosmos appearing by chance are astronomically worse than the odds of just one conscious observer, with all its sensory impressions popping into being. Therefore, if our universe is truly eternal and headed for heat death, the statistical argument suggests that the vast majority of conscious experiences should belong to these disembodied, fleeting Boltzmann brains, not to beings like us who are the product of a long, coherent cosmic history. This creates a profound crisis for cosmology. If the theory that leads us to predict a heat death also implies that we are almost certainly Boltzmann brains, then we have a serious problem. How can we trust any of our observations about the universe, including the observation that there was a Big Bang and that entropy was low, if those observations are most likely just a hallucination of a spontaneously formed brain? The paradox acts as a kind of logical reductio ad absurdum, suggesting that there must be something wrong with our underlying assumptions. Perhaps the universe is not eternal and will not end in a true heat death. Maybe a new cycle will begin before Boltzmann brains become probable, as in the cyclic models we discussed. Or perhaps the universe is not infinite in extent, limiting the number of possible fluctuations. Another compelling solution comes from the theory of cosmic inflation. If the repulsive energy of the inflationary field is eternal, as many models suggest, then it continuously spawns new, low-entropy bubble universes like our own. In this inflationary multiverse, the number of legitimate, ordered universes vastly outnumbers the number of Boltzmann brains that might form in the empty gaps between them. In this scenario, it is statistically much more likely that we live in one of these real, structured universes than that we are a fleeting illusion. The Boltzmann brain paradox, for all its strangeness, serves as a crucial sanity check for our cosmic models, a hidden pattern of logic that forces us to ensure our theories of the universe's beginning and end are consistent with the simple, undeniable fact that we are here, thinking about them. If the universe is a tapestry of interconnected events, then what is the nature of the threads that weave it together? Our journey into the hidden patterns of reality now brings us to a theory that takes the idea of a discrete, pixelated cosmos to its most radical conclusion, suggesting that the very fabric of space and time might be an illusion emerging from something far more fundamental. This is causal set theory, an approach to quantum gravity that proposes a breathtakingly simple yet profound idea. Reality is not a smooth, continuous stage, but a vast collection of discrete, indivisible events, and their only defining property is their relationship to one another. To grasp the motivation for such a radical overhaul of our conception of reality, we must return to the great conflict at the heart of modern physics. Einstein's general relativity describes the universe as a dynamic, flexible fabric, a smooth continuum where mass and energy tell spacetime how to curve, and curved spacetime tells matter how to move. This picture works magnificently on large scales, yet when we zoom into the quantum realm, this smooth canvas seems to dissolve into a seething, fuzzy foam. Quantum mechanics tells us that at the tiniest possible scales, near the Planck length, the concepts of position and momentum become fundamentally uncertain. Energy fluctuates wildly, with particles popping in and out of existence. This quantum fuzziness is completely incompatible with the smooth, deterministic curvature of general relativity. When physicists try to combine the two theories, the mathematics produces infinities, screaming that our description of reality is breaking down. This suggests that spacetime itself, the very arena of physics, may not be fundamental. It must be made of something else, something that can account for both the smooth geometry we see on large scales and the fuzzy quantum behavior at small scales. Causal set theory offers a starkly elegant solution. It proposes that the fundamental building blocks of the universe are not particles or fields, but simple, structureless events or atoms of spacetime. Imagine each event as a single point. These points are not located in space and time. Instead, they are the raw material from which space and time are constructed. What gives this collection of points this causal set? Its structure is not their position, but the causal relationships between them. One event can either precede another, follow it, or be completely unrelated. If event A can influence event B, perhaps by a photon traveling from one to the other, then we say A is in the causal past of B. This creates a web of connections, a vast, cosmic network of before and after relationships. The hidden pattern of the cosmos, according to this theory, is this intricate web of causality itself. The most astonishing consequence of this idea is that the familiar, continuous geometry of spacetime, the distances between objects and the durations between events, is not a primary feature. It is an emergent, approximate property that arises from the pattern of connections within the causal set. Think of it like a digital photograph. Up close, the image is just a grid of individual pixels, each one a single point of color. But when you zoom out, those pixels blend together to create a smooth, continuous picture. In the same way, the smooth, four-dimensional spacetime of our experience is a large-scale illusion that emerges from the underlying, discrete network of causal links. The geometry we measure with rulers and clocks is a secondary effect, a consequence of the density and arrangement of these fundamental events. A region we perceive as dense with matter and energy corresponds to a region of the causal set with a high concentration of points and connections. An empty void of space corresponds to a sparse region of the network. This approach naturally incorporates a deep truth about our universe. The speed of light is the ultimate speed limit. In a causal set, no connection can be made faster than light allows. This built-in causality prevents paradoxes and ensures the logical structure of the universe remains consistent. The theory also provides a natural explanation for the arrow of time. The fundamental relations in a causal set are inherently directional. One event comes before another. This intrinsic order at the microscopic level could be the source of the relentless forward march of time we experience in our macroscopic world. Causal set theory doesn't just quantize space. It provides a fundamental reason for why time has a direction, rooting it in the asymmetric nature of cause and effect. Of course, such a profound reimagining of reality comes with significant challenges. The primary task for proponents of the theory is to show, with rigorous mathematics, how the familiar laws of general relativity and quantum field theory can be recovered as approximations from this sparse network of causal links. This is an active area of research, and while there has been promising progress, A complete derivation remains elusive. Furthermore, the theory is notoriously difficult to test experimentally. Probing the Planck scale directly is far beyond our current technological capabilities. However, some researchers hope that certain cosmological observations, such as subtle deviations in the behavior of high-energy cosmic rays or specific signatures in the cosmic microwave background, might one day reveal the granular structure of spacetime predicted by the theory. Causal set theory presents a universe where the deepest pattern is not a shape or a symmetry, but a vast, evolving network of relationships, suggesting that the true substance of reality is not stuff, but connection. From the idea that reality's fundamental substance might be a network of causal relationships, we now turn to a theory that proposes a different kind of underlying pattern, one not of physics but of information and habit. This is the concept of the morphogenetic field, a speculative but fascinating idea that suggests the forms and behaviors we see in nature, from the unfolding of a fern frond to the instincts of a migrating bird are guided by invisible, non-physical fields that carry a kind of collective memory. The biologist Rupert Sheldrake developed this hypothesis out of a deep curiosity about one of biology's greatest mysteries, morphogenesis. How does a single fertilized egg, with its uniform DNA, manage to divide and differentiate into the incredibly complex and specific tissues of a complete organism? How do skin cells know to become skin, and heart cells know to become heart, all ending up in exactly the right place? The standard explanation points to the genetic code and complex biochemical signaling. But Sheldrake argued that genes alone are like a recipe without a chef. They specify the ingredients, the proteins, but they don't contain the spatial blueprint or the formative energy that arranges those ingredients into a specific, three-dimensional shape. He proposed that this guiding influence comes from a morphogenetic field, a term meaning form-generating field. This field is not a material force like electromagnetism, but an invisible organizing pattern, a habit of form that has been built up by previous similar systems. To make this abstract idea more tangible, think about how a habit works in your own life. The first time you drive to a new workplace, you have to concentrate, consciously noting every turn. But after doing it repeatedly, the route becomes automatic. You can drive there almost without thinking. Sheldrake suggests that nature itself operates on a similar principle of habit. The first time a new protein folds into its complex shape, or the first time a particular crystal structure forms, it might be a random, difficult process. But once it happens, a morphogenetic field is established, making it easier for the same pattern to happen again elsewhere. This process, which Sheldrake calls morphic resonance, means that the more often a pattern occurs, the more probable it becomes for that pattern to recur, not through direct communication, but through a kind of influence across space and time that connects similar things. A molecule of a new synthetic chemical, for instance, might be very difficult to crystallize the first time. But once it is achieved in one lab, the theory predicts it should become easier to crystallize in labs all over the world, as the morphic field for that crystal form strengthens and spreads. Sheldrake extends this concept far beyond biology into the realm of behavior and even human learning. He points to documented cases where animals of a certain species seem to learn a new behavior more quickly once other animals have mastered it, even when they are isolated from them. The famous example is of blue tits in Britain learning to puncture the foil caps of milk bottles to drink the cream. This behavior appeared spontaneously in different locations and seemed to spread much faster than could be explained by individual observation alone. In human terms, Sheldrake has suggested that morphic resonance might explain why some abstract concepts or difficult techniques in mathematics or music become easier for subsequent generations to grasp, as if a collective learning field builds up over time. This offers a radical alternative to the conventional view that all information is stored materially in the brain. proposing instead that memory itself might be resonant with similar patterns from the past, with the brain acting more like a tuning receiver than a hard drive. When we consider the cosmos, the theory takes on an even grander scale. Could the large-scale structures of the universe, like the elegant spiral arms of galaxies, also be influenced by morphic fields? Sheldrake has entertained this possibility, suggesting that the laws of nature might not be fixed and eternal, but more like deeply ingrained habits. The specific gravitational constant, or the mass of an electron, might be stable because these patterns have been reinforced over billions of years of cosmic evolution. This perspective challenges the very foundation of modern physics, which assumes immutable laws. Instead, it presents a universe that is organic and evolving, where patterns of form and behavior are not decreed by fixed mathematics, but are shaped by a cumulative memory, a learning process inherent to the cosmos itself. It is crucial to acknowledge that the theory of morphic fields lies firmly outside the mainstream of contemporary science. The primary criticism is the lack of a proposed mechanism that fits within the known laws of physics. How does this resonance work? What is the medium through which this information is transmitted? Mainstream science prefers explanations grounded in well-established forces and material interactions, and Sheldrake's ideas have been met with significant skepticism for appearing untestable or for relying on anecdotal evidence. However, Sheldrake himself has proposed experiments, such as testing whether people can sense when they are being stared at from behind or whether new crystal forms truly do become easier to create globally after their initial discovery. While some of these experiments have yielded positive results, they remain controversial and have not been widely replicated to the satisfaction of the broader scientific community. Despite its controversial status, the theory of morphic fields offers a profoundly different lens through which to view the hidden patterns of the universe. It suggests that the order we perceive is not just a passive consequence of physical laws, but may be an active, evolving process of memory and habit, connecting all of nature in a web of invisible influence that resonates across time and space. While many cosmic models end in cold, silent dissolution, one theory dares to propose a finale of unparalleled life and consciousness, a destiny so grand it resurrects a concept many thought science had left behind: purpose. This is the Omega Point theory, a breathtaking hypothesis formulated by physicist and cosmologist Frank Tipler. It paints a picture of the universe not as a dying ember, but as a phoenix destined to achieve a state of God-like omniscience, a final singularity where information processing becomes infinite, and the cosmos attains a form of divinity. The hidden pattern here is not a geometric shape or a vibrating string, but a teleological arrow, a universe evolving with a goal, and that goal is the ultimate triumph of mind over matter. Tipler's argument begins by embracing a specific, and quite dramatic, cosmic fate, the Big Crunch. He posits that the current acceleration driven by dark energy will eventually reverse. At some point far in the future, the expansion of the universe will halt and contraction will begin, leading to a final, cataclysmic collapse. But Tipler saw this not as an end, but as the necessary engine for an unimaginable transformation. As the universe contracts, the available energy becomes increasingly concentrated. This rising energy density would allow for exponentially more complex computations to be performed. Intelligent civilizations, which Tipler argues are an inevitable product of cosmic evolution, would not simply perish. Instead, they would harness this ever-increasing energy to fuel vast computational processes. These processes would become the central activity of the cosmos, accelerating as the collapse proceeds. Life and intelligence would essentially take control of the universe's final moments, guiding the collapse to ensure it progresses in a smooth, orderly fashion, avoiding chaotic rips and tears in spacetime that would terminate the process prematurely. This guided collapse is absolutely crucial to the theory, as it creates the conditions for an infinite amount of information processing to occur in a finite amount of time. The mechanics of this are rooted in computer science, specifically in the concept of divergent series. Imagine you have a computer that needs to perform an infinite number of calculations. This seems impossible within a finite time frame. However, if you can make the computer run faster and faster, doubling its speed with each subsequent calculation, you can complete an infinite series of calculations before a final deadline. Tipler applies this logic to the cosmos. As the universe collapses toward the final singularity, the omega point, the energy available for computation, increases without bound. An eternal intelligence, which Tipler identifies as a vastly scaled-up emulation of all conscious beings that ever lived, could use this energy to perform an infinite number of logical operations. It would experience a subjective eternity of thought and experience, all compressed into the objective, finite time leading up to the final singularity. In this view, the universe becomes a cosmic computer, and its ultimate purpose is to run the ultimate simulation, a perfect resurrection of every possible consciousness. This is where the theory makes its most audacious leap, blending cosmology with theology. Tipler argues that this final, omniscient, omnipotent, and eternal intelligence fulfills the traditional attributes of God. It is not a God from outside the universe, but one that emerges from within it through physical law. The omega point would possess complete knowledge of the entire history of the cosmos, as its infinite computational power would allow it to simulate every possible past state with perfect accuracy. This leads to a profound and deeply personal implication. The omega point could and would resurrect every single person who has ever lived. It would recreate your consciousness, your memories, your entire subjective experience, and maintain that simulation forever within its infinite mind. Death in this framework is not a final end, but a temporary state before a final, universal resurrection. The hidden pattern of cosmic evolution, therefore, is a journey toward salvation through physics, where the laws of nature themselves guarantee a form of eternal life. Naturally, a theory of such sweeping ambition faces formidable scientific challenges. The most significant is its reliance on a big crunch scenario. Current observational evidence strongly suggests that dark energy is not weakening but may be constant or even strengthening, pointing toward an eternal expansion and a heat death, not a collapse. Tipler's model requires a closed universe with specific parameters that currently seem disfavored by data. Furthermore, the idea of intelligent life guiding the collapse of the entire universe involves technologies and a control over cosmic forces that stretch the limits of plausibility. Critics argue that the theory, while mathematically intriguing, rests on a chain of highly speculative assumptions, each of which must be true for the grand conclusion to hold. It stands as a powerful, provocative thought experiment that forces us to consider the ultimate potential of intelligence in the cosmos, a daring vision of a universe where consciousness is not a fleeting accident, but the central character in its own epic story of redemption and eternal becoming. While we grapple with the universe's possible fate and its deepest structure, there is a theory that challenges perhaps our most intimate experience of reality, the feeling that time flows. This is the concept of the block universe, a view drawn directly from the equations of Einstein's general relativity, which suggests that the past, present, and future are not sequential but exist all at once, permanently fixed in a single, four-dimensional structure. In this eternalist perspective, the hidden pattern of existence is not a process unfolding, but a completed tapestry where every event, from the Big Bang to the last flicker of the last star, is equally real. To understand this radical idea, we must first step away from our intuitive sense of time as a river flowing from the past, through the present, and into the future. This feeling is powerful and undeniable, but physics asks us to consider a different picture. Einstein's theory fused space and time into a single entity, space-time. In this framework, An event isn't just something that happens at a point in space. It happens at a specific coordinate in spacetime. Crucially, the theory treats all these coordinates as equally valid. There is no special marker in the equations that singles out now as anything more significant than then or later. From this viewpoint, the universe can be imagined as a vast, four-dimensional block, a cosmic loaf of bread where each slice represents the entire universe at a single moment. But unlike a real loaf where we eat one slice at a time, the block universe proposes that all the slices exist simultaneously. Your birth, you watching this video, and every moment of your future are all just as real as the dinosaurs roaming the Earth or the formation of distant solar systems. They are simply located at different coordinates within the block. This notion finds powerful support in the relativity of simultaneity, one of Einstein's most famous conclusions. Imagine two lightning bolts striking the ends of a moving train. An observer standing on the platform might see the bolts strike simultaneously, but an observer on the train, moving toward one bolt and away from the other, will see the forward bolt strike first. There is no absolute, universal answer to the question, did they happen at the same time? The concept of now is not a universal truth but depends on your frame of reference. If there is no privileged now, then it becomes difficult to argue that the present is any more real than the past or future. What is the past for one observer could be the future for another. The block universe elegantly resolves this by making no distinction. All times are equally existent, just as all points in space are equally existent. You don't say that New York is more real than London because you happen to be there. In the same way, the block universe suggests that Tuesday is no more real than last Tuesday or next Tuesday. The philosophical implications of this are profound and deeply unsettling, particularly for our understanding of free will. If the future already exists in a fixed, unchangeable state, then what does it mean to make a choice? It feels as though we are authors of our own lives, but eternalism suggests we are merely readers following a story that has already been written. Every decision you believe you will make tomorrow is, from the perspective of the block, already etched into the fabric of spacetime. This can feel like a form of cosmic determinism, where the illusion of free will is a necessary part of the narrative experienced by the conscious beings within the block. However, some philosophers argue that this is a misunderstanding. They suggest that free will isn't about changing the future, but about our actions being the cause of what happens next. In the block, your choices are still the reasons for subsequent events. They are just part of the fixed, causal structure of the whole. Your life is not a pre-recorded movie you are forced to watch passively. It is more like a novel in which you are the main character. The story is complete, but your choices within it are still authentically yours, woven into the immutable narrative. This perspective can be strangely liberating. It invites us to see our lives not as fleeting moments rushing toward oblivion, but as permanent features of the cosmos. Every triumph, every moment of love, every act of courage is eternally real, its value undiminished by the passage of time. From this grand, four-dimensional vantage point, the universe reveals a pattern of breathtaking completeness. It is not becoming, it simply is. The flow of time we feel so acutely may be the way our consciousness navigates this eternal structure, like a spotlight moving across a vast, intricate sculpture, illuminating one part at a time while the whole masterpiece remains, forever whole and unchanging. This concept of a self-regulating system takes on a deeply personal dimension when we look not at the far reaches of the cosmos, but at the world beneath our feet. Shifting our gaze from the cosmic block to our own living planet, we encounter a theory that suggests the most profound hidden pattern might be the one sustaining our very existence. This is the Gaia hypothesis, a revolutionary idea that proposes Earth itself functions as a single, vast, self-regulating system, where life is not just a passenger on a planetary rock, but an active participant in steering the global environment. The hypothesis was formulated in the 1970s by chemist James Lovelock, with significant contributions from microbiologist Lynn Margulies. Lovelock was originally working with NASA on methods to detect life on Mars. He reasoned that a planet with life would have an atmosphere far from chemical equilibrium, because living organisms constantly consume and release gases in ways that would be highly improbable through geology alone. For example, Earth's atmosphere contains large amounts of both reactive oxygen and methane, which should quickly react with each other and disappear unless they are being continuously replenished by biological activity. Mars, by contrast, has an atmosphere in a near-perfect state of chemical equilibrium, a quiet and stable mixture that suggests a lifeless world. From this insight, Lovelock and Margulies developed a much grander vision. They proposed that the entire biosphere, all living things, interacts with the atmosphere, oceans, and geology to form a complex, synergistic system that actively maintains the conditions for life's continuation. They named this system Gaia, after the ancient Greek goddess of the earth. The evidence for this self-regulation is found in some of the most fundamental patterns of our planet's history. Consider the faint young sun paradox. Models of stellar evolution show that the Sun was about 30% dimmer billions of years ago. With so much less energy arriving from the Sun, the Earth should have been a frozen ball, making the emergence and evolution of life nearly impossible. Yet, the geological record shows abundant evidence of liquid water and life dating back to that very period. The Gaia hypothesis offers an explanation. Early life forms, particularly microbes, helped regulate the planet's temperature. They may have produced greenhouse gases like methane and carbon dioxide at a rate that created a thicker atmosphere, trapping just enough heat to keep the planet habitable. As the Sun grew brighter over billions of years, the biosphere responded by drawing down carbon dioxide, preventing a runaway greenhouse effect like the one that scorched Venus. This is not a conscious plan, but an emergent property of the feedback loops between life and its environment. Another stunning example is the salinity of the oceans. Rivers constantly wash salts from the land into the sea. If this process continued unchecked, the oceans would become progressively saltier, eventually reaching a level that would be toxic to most marine life. Yet, the salinity of the oceans has remained relatively stable at around 3.4% for hundreds of millions of years. The Gaia hypothesis suggests that life itself helps manage this balance, perhaps through the formation of salt marshes or other biological processes that sequester salt. This leads to the most controversial and philosophically rich aspect of the hypothesis. Does this self-regulation imply a form of planetary intelligence or purpose? The strong interpretation of Gaia sees the Earth as a kind of superorganism, a single, integrated entity with properties that cannot be predicted by studying its parts in isolation. In this view, the stability of the climate and atmospheric composition is not a lucky accident, but a form of homeostasis, similar to how your body maintains a constant temperature despite changes in the weather. This perspective can feel almost spiritual, suggesting a deep, intrinsic wisdom in the natural world. The weak interpretation, which is more widely accepted in the scientific community, views Gaia not as an organism, but as a complex system with tight feedback loops. In this view, there is no foresight or goal. The regulation is a simple consequence of Darwinian natural selection operating on a planetary scale. If a particular type of organism happens to alter the environment in a way that makes that environment more favorable for life in general, and for itself in particular, it will thrive. Organisms that destabilize their environment tend to go extinct, leaving behind a biosphere that is, by default, composed of life forms that are good at creating stable conditions. It is a system that appears designed because all the failed experiments have been filtered out by billions of years of trial and error. This idea of planetary-scale feedback loops has profound implications for our search for life beyond Earth. If the Gaia hypothesis is correct, then a living planet should betray its presence through atmospheric disequilibrium. When we point our telescopes at distant exoplanets, one of the key signs we will look for is a chemical imbalance in their atmospheres, an abundance of gases that react with each other and should not coexist without a continuous biological source. This makes Gaia not just a theory about Earth, but a potential guide for astrobiology, a template for the hidden patterns that might signify a living world. It suggests that life, wherever it arises, will not be a passive bystander. It will inevitably become entangled with its planet's geology and climate, weaving itself into the fabric of the world and leaving a distinct, detectable signature of its activity. The pattern of a living planet may be one of dynamic instability held in a miraculous, persistent balance, a delicate dance between biology and geology that transforms a mere rock into a vibrant, breathing world. While the block universe presents a static, four-dimensional picture of reality, a different interpretation of quantum mechanics proposes a cosmos that is not just vast, but perpetually multiplying, endlessly birthing new versions of itself with every fleeting moment. This brings us to the mind-bending many worlds interpretation, a theory that suggests the ultimate hidden pattern of existence is not a single tapestry, but an infinite, ever-branching tree of parallel realities where every possible outcome is realized. To understand the profound shift this idea represents, we first need to confront the central weirdness of quantum mechanics that it attempts to resolve, the problem of measurement. In the quantum realm, particles like electrons don't have definite properties until we measure them. An electron isn't simply spinning up or down like a tiny top. Instead, it exists in a blurry superposition, a mixture of all possible states simultaneously. It's only when a scientist sets up a detector and makes an observation that this fuzzy cloud of possibilities seems to collapse into a single, definite outcome. The traditional explanation, championed by Niels Bohr and known as the Copenhagen interpretation, treats this collapse as a fundamental yet mysterious process. It draws a sharp line between the quantum world, governed by probability waves, and the classical world of definite objects, without fully explaining how or why the act of observation causes the wave to collapse. This has always been deeply unsatisfying to many physicists. Why should consciousness or measurement have such a privileged, almost magical, role in shaping reality? In 1957, a young physicist named Hugh Everett offered a radical alternative. He proposed that the wave function, the mathematical description of a quantum system, never actually collapses. There is no special division between the quantum and classical worlds. Instead, every single possible outcome encoded in a superposition does, in fact, happen. The reason we only experience one outcome is that the universe itself splits, branching into multiple, non-communicating parallel worlds. Imagine you are about to perform a simple experiment on an electron in superposition. You set up your detector. At the precise moment of measurement, the universe divides. In one branch, you see the electron spin up and record the result. In another, completely separate branch, an identical version of you sees the electron spin down. Both outcomes are equally real. Both versions of you are equally real. They simply proceed to live their lives in their own independent timelines, completely unaware of each other. This idea transforms probability from a measure of chance into a measure of personal experience. When we say there is a 50% chance of an electron spinning up, we are not describing an inherent randomness in the universe. We are describing the fraction of future branches, the proportion of parallel worlds, in which a version of us will see that particular result. Your entire life's history is just one path you have taken through this immense, branching tree of reality. But at every moment, at every quantum decision point, and there are trillions occurring every second in every atom, countless other versions of you are living out the roads not taken. The version of you who turned left instead of right, who said yes instead of no, who caught the train they just missed, all exist in their own equally valid universes. The hidden pattern is not one of chance, but of plenitude, a cosmos of limitless possibility where everything that can happen does happen. The implications for identity are staggering. The concept of a single, continuous self begins to dissolve. You are not a solitary thread, but a constantly fraying bundle of threads, each weaving a different tapestry. There is no you in the singular sense. There is a vast ensemble of yous, a multiverse of individuals who shared a common, passed up to a certain point, and then diverged forever. This perspective offers a strange resolution to philosophical puzzles about free will and destiny. In a sense, you have all the free will in the world, because every possible choice you could make is made by some version of you. Yet, from the perspective of any single branch, your path feels uniquely determined. The many worlds interpretation doesn't abolish causality, it universalizes it, ensuring that every causal possibility is fulfilled somewhere in the multiverse. Critics of the theory point to its immense, some would say extravagant, ontological cost. It seems to violate Occam's razor, the principle that we should not multiply entities beyond necessity. Are we really to believe that an entire universe, complete with galaxies and stars and histories, duplicates itself with every quantum event? Proponents argue that this is actually more parsimonious than the Copenhagen interpretation because it removes the need for an ad hoc, unexplained process of wave function collapse. The mathematics becomes cleaner and more continuous. The real challenge, however, is testability. Since the different branches do not interact, how could we ever obtain evidence for other worlds? Some physicists speculate that if the branching is not perfectly clean, there might be tiny, residual interactions between worlds, perhaps leaving a faint signature in certain experiments. But for now, the theory remains a compelling, if unproven, framework. It presents a cosmos of breathtaking richness, a hidden pattern of endless divergence where reality is not a single story but an infinite library containing every story that can ever be told. Yet even as we contemplate a reality of infinite branching worlds, we are reminded that our observations of this one universe can still yield deeply puzzling results. Our journey now takes a turn toward a finding so peculiar it was given a name straight out of a science fiction thriller: the axis of evil. This is not a cosmic malevolent force, but a chillingly unexpected pattern discovered in the most pristine map of the early universe. We possess the cosmic microwave background radiation. This faint glow is the leftover heat from the Big Bang, a snapshot of the universe when it was just 380,000 years old. For decades, it has been the cornerstone of modern cosmology, its stunning uniformity providing the strongest evidence for the Big Bang and its tiny fluctuations seeding all the galaxies we see today. But when scientists created exquisitely detailed maps of this radiation, they noticed something that, according to our most cherished assumptions, should not be there. The anomaly revolves around a fundamental pillar of cosmology known as the cosmological principle. This principle states that on the largest scales, the universe is isotropic and homogeneous. Isotropy means it looks the same in every direction, like the view from a boat in the middle of a calm ocean. Homogeneity means it has a roughly uniform distribution of matter when viewed on a sufficiently grand scale, like realizing that from high above, the ocean is made of the same water everywhere. This principle is not just a philosophical preference. It is the foundational assumption that allows us to apply the same laws of physics across the cosmos, and to use our local observations as a fair sample of the whole. It is the reason we can even attempt to write a history of the universe. The cosmic microwave background radiation is the ultimate test of this principle, and for the most part, it passes with flying colors, appearing as a nearly perfect blanket of uniform temperature. However, when researchers looked closer at the larger scale patterns within this blanket, they found a hint of a preferred direction, a whisper of a cosmic axis. The so-called axis of evil refers to an unexpected alignment of several large-scale features in the microwave background. First, There is the alignment of the quadrupole and octupole moments. These are technical terms for the simplest ways the temperature map deviates from perfect uniformity. The quadrupole represents the most basic egg-shaped deviations, while the octupole represents more complex, cloverleaf-like patterns. In a truly random, isotropic universe, these patterns should be oriented randomly with respect to each other. But analyses, particularly from the Wilkinson microwave anisotropy probe, suggested their orientations were oddly aligned. Even more strangely, this alignment itself seemed to be correlated with the ecliptic plane of our own solar system and the direction of our motion through the cosmos. It is as if the largest structures in the observable universe are subtly pointing back at us, a finding that makes cosmologists deeply uncomfortable because it hints that our location in the cosmos might not be so typical after all. This is the antithesis of Copernican humility. It suggests we might be at the center of a cosmic pattern. Naturally, the scientific community has approached this anomaly with extreme caution, exploring every possible mundane explanation before entertaining the idea of a revolutionary discovery. The primary suspect is always systematic error. Could some aspect of the spacecraft's instrumentation, or an unaccounted-for foreground emission from within our own galaxy, be imprinting this false signal onto the data? Teams have spent years painstakingly analyzing and subtracting potential contaminants, from galactic dust to solar system emissions. While some features of the anomaly have become less prominent with more precise data from the Planck satellite, the strange alignments have not completely disappeared, continuing to linger at a low level of statistical significance. This puts cosmologists in a difficult position. The signal is not strong enough to definitively declare a crisis in physics, but it is persistent enough to refuse to go away entirely, like a faint, unexplained noise in the dead of night. If the axis of evil is not an error, then we are left with two other profound possibilities. The first is that it is a colossal statistical fluke. Our observable universe is, after all, just one sample. When you roll cosmic dice a nearly infinite number of times across the multiverse, a few universes will, by sheer chance, exhibit weird, large-scale alignments. We might simply live in one of those oddball cosmoses. The second, and far more radical, possibility is that the anomaly is real. This would mean the cosmological principle is wrong, at least on the scale of our observable universe. Our cosmic horizon might not be a fair sample. We could be living in a region that is genuinely anisotropic, perhaps because the process of inflation that blew up our patch of spacetime was not perfectly uniform. Alternatively, the alignment could be a sign of something even more exotic, like the influence of a universe that existed before our Big Bang, whose structure left a ghostly imprint on our own, or a truly universal preferred direction that would force us to rewrite Einstein's theory of gravity itself. The axis of evil remains one of the most tantalizing and unresolved mysteries in cosmology, a quiet challenge to our deepest assumptions, and a reminder that the universe may still have a few profound secrets left to reveal. From the strange alignments of the axis of evil, we now turn to a theory that finds a hidden pattern not in the silence of space, but in a concept that has captivated humanity since its very beginning, the idea of a cosmic music. This is the law of octaves and the pursuit of cosmic harmonies, an ancient intuition that the universe is not just governed by mathematics, but is fundamentally musical in nature, with the movements of the heavens and the building blocks of matter all conforming to the same principles of vibration and resonance that create a beautiful chord. The seed of this idea was planted over 2,000 years ago by the Greek philosopher and mathematician Pythagoras. The story goes that one day, passing by a blacksmith's shop, he noticed that hammers of different weights produced distinct, harmonious tones when struck against the anvil. Intrigued, he experimented further, possibly with strings of varying lengths stretched under tension. He discovered that when you pluck a string, it produces a specific note. If you divide the string in half, The new note is an octave higher, the same fundamental tone, but vibrating at double the frequency. Other simple ratios produced other harmonious intervals. A ratio of 3:2 gave the perfect fifth. A ratio of 4:3 the perfect fourth. Pythagoras was struck by a profound realization. Harmony, something we experience as beautiful and emotionally resonant, was not a vague, mystical quality. It was a direct and measurable consequence of simple, elegant mathematics. He and his followers extended this insight to the cosmos itself, proposing that the planets, as they moved through the heavens, must also produce tones based on their speeds and distances. They believed that a music of the spheres was constantly playing, a celestial symphony too sublime for our mundane ears to perceive, but whose mathematical harmony was the very principle of cosmic order. This Pythagorean dream was revived with a new scientific rigor centuries later by the German astronomer Johannes Kepler. A man living at the crossroads of mysticism and the emerging scientific revolution, Kepler was utterly convinced that God had created the universe according to a geometric and harmonic plan. He possessed something Pythagoras did not: the incredibly precise planetary observations of his mentor, Tycho Brahe. Kepler spent years trying to fit Tycho's data into the ancient model of perfect circles and crystalline spheres, but the numbers simply would not cooperate. He eventually discovered his famous 3 laws of planetary motion, which showed that planets move in ellipses, not circles, and that their speeds vary. Yet, even as he embraced these new, less-than-perfect shapes, he never abandoned his search for an underlying harmony. In his work Harmonices Mundi, The Harmony of the World, he made one final, breathtaking attempt. He compared the maximum and minimum orbital speeds of the planets as they traveled their elliptical paths. For instance, he found that Saturn's speed varied in a ratio that was almost a perfect fourth, while Jupiter's speeds created a minor third. He even assigned musical notes to each planet, composing a short, actual melody for the solar system. While the harmonies were not perfectly precise by our modern standards, the impulse was powerful. For Kepler, the fact that the messy, real-world data even approximated these musical intervals was proof of a divine composer, a hidden pattern of resonance written into the very laws of motion. The modern incarnation of this ancient idea finds its most sophisticated expression in string theory. As we explored earlier, this framework proposes that the fundamental constituents of reality are not point-like particles, but tiny, vibrating loops of energy. The different vibrational modes of these strings, the specific frequencies and harmonics at which they resonate, determine the properties of the particles we observe. An electron is simply a string vibrating one way. A quark is the same string vibrating another way, much like a single violin string can produce a G, a D, or an A. In this view, the entire universe is a cosmic symphony. The forces of nature, gravity, electromagnetism, the nuclear forces, are not separate entities but different sections of this grand orchestra, all emerging from the collective vibrations of countless strings. The hidden constants of physics, the numbers that seem so finely tuned, may simply be the required notes for a stable, coherent melody to exist. The law of octaves, which Pythagoras discovered on a simple monochord, is scaled up to an unimaginable degree, governing the very frequencies that give rise to space-time and matter. The cosmic harmony is no longer a metaphorical music for the spheres, but a literal description of the fundamental level of reality. This perspective suggests a deep, perhaps ultimate, connection between mathematics, music, and physics. The reason our minds can comprehend the universe mathematically might be because the universe is, at its core, a vibrational structure. Our attraction to musical harmony could be more than a cultural artifact. It might be a reflection of our own constitution from these same vibrational principles. When we hear a consonant chord, our brains may be recognizing a pattern that is woven into the fabric of existence itself. a pattern of simple, stable ratios that allow for complex structures to form without collapsing into chaos. From the energy levels of an atom, which can be understood as a harmonic oscillator, to the orbital resonances that stabilize planetary systems, the same language of frequency and resonance appears again and again. The hidden pattern is one of vibration, a universal tendency for systems to find stable, resonant states. It is a theory that unites the microcosm and the macrocosm through the common thread of music, proposing that we live in a universe that is not silent, but is perpetually humming with the energy of its own existence, a symphony whose notes are the atoms and whose movements are the galaxies. But how does a cosmos of infinite branching possibilities, where every outcome is real, translate into the single, concrete reality we all collectively experience? Why, when we look at a chair, do we all agree it is solid and in one place, when quantum mechanics suggests it is a cloud of probabilities? This puzzle lies at the very heart of the quantum measurement problem, and one of the most compelling solutions suggests the answer lies in a process surprisingly similar to the one that shaped life on Earth. This is the theory of quantum Darwinism, which proposes that the hidden pattern leading to our definite world is a form of natural selection, where the most robust quantum states survive by leaving the most copies of themselves. To appreciate the power of this idea, we need to revisit the strange duality of the quantum world. An isolated particle, like an electron, can exist in a superposition of states. It isn't definitively here or there, it has a probability of being in many places at once. This fuzzy existence is described by its wave function. The traditional mystery is what happens during a measurement. The act of observation seems to collapse this wave function, forcing the particle to pick a single, definite location. But why? What is so special about measurement? Quantum Darwinism, developed by theorists like Wojciech, sidesteps this question entirely. It argues that wave function collapse is an illusion. Instead, the reason we see a definite world is not because of a mysterious collapse, but because of the relentless interaction between a quantum system and its environment. Think of the environment not as a passive backdrop, but as a bustling, information-hungry witness. The air around us is filled with photons of light, molecules of gas, and countless other particles. Now imagine a simple quantum system, a single electron that is in a superposition, meaning it is both spin up and spin down. This electron is not isolated. It is constantly being bombarded by photons from the room's light, by air molecules bouncing off it. Each of these tiny interactions is like a miniature measurement. A photon scattering off the electron will do so differently depending on whether it encounters an electron that is spin up or spin down. In doing so, the photon encodes information about the electron's state. But here is the crucial part. The photon doesn't just record this information and keep it to itself. It then flies away and interacts with other parts of the environment, effectively making a copy of that information. Then another photon does the same, and another. Very quickly, countless copies of the information about the electron's state are broadcast throughout the environment. This is where the Darwinian analogy takes hold. The different possible states of the electron, spin up and spin down, are like competing variations in a population. But they are not competing for food or mates. They are competing to leave the most informational offspring. A state that is fragile and easily disrupted by the environment will not produce clean, replicable copies. It will be a poor propagator of information. But a state that is stable and robust in the face of environmental interaction will be measured over and over again. Its information will be copied and redistributed with incredible efficiency. These multiple, redundant copies are what make a property objective. You, me, and any other observer can each independently probe the environment. By catching a few of those photons with our eyes, for instance, and we will all access the same information. We will all agree the electron is spin up. The state that becomes objective reality is not the one that is somehow, chosen by consciousness, but the one that is the fittest at proliferating its information throughout the environment. The hidden pattern is a cosmic survival of the fittest, where reality is defined by what is most effectively and widely observed. This process, known as decoherence, explains why we don't see macroscopic objects in superposition. A chair is made of trillions upon trillions of atoms. Each atom is constantly interacting with the environment, and those interactions select for definite states. For the chair to be in a quantum superposition of being both here and there, every single one of those atoms would have to be perfectly isolated from the environment simultaneously, which is practically impossible. The environment acts as a continuous monitoring system, constantly measuring the chair and ensuring that only the fittest, most stable state, the one we perceive as the chair being firmly on the ground, leaves enough informational copies for us all to see. Quantum Darwinism thus bridges the gap between the quantum weirdness of the small and the classical certainty of the large. It suggests that the solid, dependable world we experience is solid not because it is fundamentally different from the quantum realm, but because it is the outcome of a relentless process of environmental selection. The pattern of our reality is etched not in stone, but in the countless informational impressions it leaves on the world around it. A consensus reached through a constant, silent dialogue between every object and its surroundings. This journey through the cosmos has revealed patterns of immense scale and profound subtlety, from the branching multiverse to the harmonious vibrations of strings. But what if one of the greatest mysteries in modern astronomy, the identity of dark matter, has been hiding in plain sight, not as an exotic new particle, but as the most gravitationally dominant objects we already know? This brings us to a theory that reimagines the universe's infancy and its hidden architecture, the primordial black hole hypothesis. It proposes that the unseen mass holding galaxies together is not a sea of invisible particles, but a vast population of ancient black holes, relics from the first moments of creation. To understand how black holes could form without the death of massive stars, we need to travel back to a time before any stars had even ignited. In the incredibly dense and hot soup of the universe just after the Big Bang, space itself was not smooth. It was rippling with intense fluctuations in density. Most of these ripples were small and were stretched out by the rapid expansion of cosmic inflation, eventually becoming the seeds for galaxies. But the primordial black hole hypothesis suggests that some regions were so exceptionally dense that they crossed a critical threshold. Imagine a knot in the fabric of space-time so tight and heavy that instead of smoothing out, it collapsed under its own immense gravity right then and there. These knots wouldn't need to wait for stars to form and die. They would be black holes born directly from the raw energy of the expanding cosmos. Their size would depend entirely on the mass within that collapsing region. A patch the size of an asteroid could form a black hole with the mass of a planet. A region as large as a solar system could collapse into a black hole with the mass of 1,000 suns. This process could have created a cosmic population of black holes spanning a tremendous range of masses, from microscopic to supermassive, all within the first second of existence. The hidden pattern suggested by this theory is a ghostly infrastructure woven through the cosmos. Instead of dark matter being a uniform halo of particles surrounding a galaxy, it would be a vast swarm of these primordial black holes, drifting silently through the darkness. Their collective gravity would provide the exact same scaffolding that astronomers observe, the glue that keeps galaxies from flying apart as they spin. This idea offers an elegant solution to the dark matter problem because it requires no new, undiscovered physics. We already know black holes exist and that their gravity is powerful, and aside from their gravitational pull, completely dark. They are the perfect candidate for a hidden cosmic component. This hypothesis also provides a potential answer to another profound puzzle: the origin of supermassive black holes. At the heart of nearly every large galaxy, including our own Milky Way, sits a behemoth black hole weighing millions or even billions of times the mass of our Sun. The mystery is how these giants grew so large so quickly. Observations of incredibly distant quasars, powered by supermassive black holes, show that they existed when the universe was less than 1 billion years old. It's difficult to explain how a star-sized black hole could have consumed enough matter to reach such colossal proportions in such a short cosmic time. But if a giant primordial black hole was already present, acting as a ready-made seed from the very beginning, the problem vanishes. These ancient giants would have had a massive head start, allowing them to quickly grow by accreting gas and merging with other black holes, becoming the gravitational anchors for the first galaxies. The challenge, of course, is proving it. How do you search for objects that emit no light and could be scattered across the vast emptiness between stars? Astronomers have devised clever, indirect methods. One of the most promising involves a phenomenon predicted by Einstein: gravitational microlensing. If a primordial black hole passes directly between Earth and a distant star, its gravity will act like a lens, bending the starlight and causing the star to temporarily brighten. By monitoring millions of stars in nearby galaxies like the Large Magellanic Cloud, projects like the Optical Gravitational Lensing Experiment, or OGLE, have looked for these characteristic flashes. The results have been intriguing but inconclusive, placing limits on how many planet-sized or asteroid-mass black holes could be out there. Another avenue of investigation comes from the Laser Interferometer Gravitational Wave Observatory, or LIGO, which detects ripples in spacetime from merging black holes. Some of the black holes LIGO has observed are curiously heavy, falling into a mass range that is difficult to explain through standard stellar evolution. Could these be primordial black holes that have been drifting through space since the dawn of time? Each new gravitational wave detection adds a data point to this cosmic census, helping us piece together the true population of dark, compact objects in the universe. The search for these ancient ghosts continues, a testament to our ingenuity in probing the darkest corners of the cosmos. Whether the primordial black hole hypothesis is ultimately confirmed or not, it challenges us to think creatively about the universe's beginnings. It suggests that the hidden patterns of dark matter and galactic structure might not be written in the language of unknown particles, but in the gravitational signature of the universe's very first structures, black holes that have been silent witnesses to cosmic history since the first fleeting moments of time. Delving deeper into the cyclic models we touched upon earlier, the ekpyrotic universe scenario presents a particularly elegant and dramatic version of this eternal return, one that is deeply rooted in the extra-dimensional landscape of string theory. This theory reimagines the cosmos not as a solitary universe, but as one of many vast, floating islands of reality. In this view, our entire three-dimensional existence, every galaxy, every star, every one of us is confined to a surface called a membrane, or brain for short. Think of it as an immense, flexible sheet. But this sheet doesn't drift in nothingness. It exists within a higher dimensional space known as the bulk. And crucially, we are not alone in this bulk. There is at least one other parallel brain, a companion universe floating a microscopic distance away in a dimension we cannot perceive. The central, breathtaking event in this cosmic drama is the Big Bang. But here, it is stripped of its singular, mysterious origin. Instead of a moment of infinite density erupting from a void, the ekpyrotic model proposes that our universe's beginning was a collision. The parallel brain, drawn by a force across the bulk, slowly moves toward ours. When these two colossal, three-dimensional worlds finally meet, the impact is one of unimaginable energy. This collision does not destroy the brains, instead, it's more like a cosmic clap. The immense kinetic energy of the crash is converted into heat and matter, flooding our brain with a hot, dense plasma and initiating the expansion we now call the Big Bang. After the impact, the brains rebound and move apart, and the universe we know begins its long evolution, giving rise to galaxies, stars, and eventually, life. The hidden pattern is not a one-time creation, but a rhythm of approach, collision, and separation, a cosmic season of destruction and rebirth. What makes this model so compelling is how it naturally solves some of the same puzzles that inflation addresses, but through a different mechanism. Take the horizon problem, the mystery of why opposite sides of the universe have the same temperature. In the ekpyrotic scenario, before the collision, the two brains are parallel and very close. This allows their surfaces to reach a uniform temperature through interactions across the tiny gap in the bulk. When they collide, this pre-established uniformity is imprinted onto the newborn universe, explaining the smoothness without requiring a period of faster-than-light expansion. Similarly, the violent, smoothing nature of the collision itself can account for the observed flatness of the universe, much like how stretching a wrinkled rubber sheet makes it flat. The most tantalizing aspect of this theory is the potential for evidence. If our universe was born from a brain collision, might there be a fossil record of that event? Some cosmologists believe the answer might be hidden in the cosmic microwave background. The collision would have generated immense gravitational waves, ripples in the fabric of space-time. These waves would have left a distinct, twisting pattern or polarization in the ancient light. While the search for this specific signature is ongoing and highly complex, its detection would be a monumental step toward validating this cyclic vision. The ekpyrotic universe offers a profound shift in perspective, transforming the Big Bang from a mysterious beginning into a phase in an endless cycle. It suggests that the hidden pattern of cosmic history is not a linear arrow, but a grand, eternal pendulum swing, where each new universe is born from the ashes of the last in a timeless dance of creation. Returning now to the holographic principle, we find its most powerful and famous application in solving one of the most vexing puzzles in all of physics, the black hole information paradox. This problem strikes at the very heart of our understanding of reality, creating a direct conflict between the two pillars of modern physics, Einstein's general relativity and quantum mechanics. To understand the paradox, we need to think about what happens when you throw something into a black hole. Imagine you have a book, a very special book that contains a vast amount of information. It could be an encyclopedia, a diary, or even a hard drive full of data. According to the pristine rules of quantum mechanics, information can never be truly destroyed. It can be scrambled, encoded, or transformed, but it must be conserved. It is a fundamental tenet of the universe, as sacred as the conservation of energy. Now, you toss this book into a black hole. From the perspective of general relativity, the book crosses the event horizon, the point of no return, and is inexorably pulled toward the central singularity, where it is crushed out of existence. The information it contained seems to have vanished from our universe forever, which quantum mechanics insists is impossible. This is the core of the paradox. The plot thickened dramatically with Stephen Hawking's groundbreaking work. He showed that black holes are not entirely black. Due to quantum effects near the event horizon, they slowly radiate energy, a faint glow now known as Hawking radiation. This radiation causes the black hole to lose mass and eventually, over eons, evaporate completely. The problem is that Hawking radiation is thermal. It is random heat energy. It appears to carry no information about what fell into the black hole. Whether you threw in a book, a grand piano, or a barrel of radioactive waste, the Hawking radiation coming out would be exactly the same, a featureless hiss of particles. So, when the black hole finally vanishes, what happens to the unique information contained in the original objects? If the information is not in the radiation and not in the black hole, it seems to have been erased from existence, violating a cornerstone of quantum theory. For decades, this presented a glaring contradiction. suggesting that our most fundamental theories were incomplete. The holographic principle swoops in as an elegant rescuer. Recall that the principle suggests all the information about a three-dimensional volume can be encoded on its two-dimensional boundary. For a black hole, that boundary is its event horizon. The principle reimagines the fate of our book. When it falls toward the black hole, it doesn't simply vanish. Instead, as it approaches the event horizon, its information is not lost but is smeared and imprinted onto the horizon itself, like a cosmic fingerprint. The event horizon becomes a vast, frenetically active surface, a holographic plate recording every detail of what has fallen in. This encoding happens at an unimaginably fine scale, at the Planck length, turning the horizon into the universe's most dense hard drive. Then, as the black hole emits Hawking radiation, this process is not random. The radiation subtly interacts with this encoded data on the horizon. The information is not carried away in the radiation itself, but the radiation's properties are influenced by the information on the boundary. It's an incredibly complex and slow process, like a cosmic shredder working in reverse, where the scrambled information on the horizon is gradually teased out and released back into the universe as the black hole evaporates. By the time the black hole is gone, the information has, in principle, been returned, preserving the sacred rule of quantum mechanics. This resolution profoundly deepens the idea that information is the most fundamental hidden pattern of reality. It suggests that what we perceive as solid matter, the book, the piano, the stars, might be a secondary manifestation. The true, primary substance of the universe is information. The laws of physics are not laws governing particles and forces, but laws governing the manipulation, transmission, and conservation of information. The universe, in this view, is not a collection of things, but a network of relationships and data. The holographic principle, by solving the black hole information paradox, doesn't just fix a technical problem in physics. It offers a radical new ontology. It tells us that the solidity of the world is an illusion, a three-dimensional projection from a vast, two-dimensional store of cosmic data, and that the deepest pattern we can discern is the endless, intricate dance of information itself. This staggering vision of a multiverse finds one of its most mathematically grounded expressions within the very framework we just explored. If string theory is the candidate for a final theory, then it may also be the key that unlocks the door to an almost limitless plurality of worlds. This leads us to the concept of the string theory landscape, a truly mind-boggling idea that suggests the hidden pattern of reality is not one of elegant unity, but one of breathtaking, almost unfathomable diversity. You'll recall that for the mathematics of string theory to work, the 6 extra spatial dimensions must be curled up into a specific, tiny geometric shape known as a Calabi-Yau manifold. For decades, physicists hoped there would be only one unique way to do this, leading to one unique set of physical laws that would perfectly describe our universe. That was the dream of a single, elegant theory of everything. However, as researchers delved deeper, they made a shocking discovery. The number of ways these extra dimensions can be compactified is not 1 or a dozen or even a million. The number is astronomically vast, estimated to be around 10 to the power of 500. That's a 1 followed by 500 zeros, a number so large it exceeds the number of atoms in the entire observable universe. Each distinct way of curling up these dimensions corresponds to a different vacuum state, a different possible set of laws of physics. One configuration might yield a universe with a strong nuclear force a fraction weaker, preventing atoms from ever forming. Another might produce a gravitational constant so powerful that any stars that did form would collapse instantly into black holes. Each point in this cosmic landscape represents a different possible universe with its own unique physical constants. This revelation fundamentally transforms the question of why our universe is the way it is. For centuries, scientists have been baffled by the apparent fine-tuning of the constants of nature. The strength of gravity, the mass of the electron, the cosmological constant, if any of these were even slightly different, the universe would be sterile, incapable of supporting the complex structures necessary for life. From the perspective of a single universe, this seems like an incredible coincidence, a miracle. But within the landscape of string theory, this fine-tuning is explained not by design, but by a simple selection effect. In a landscape of 10 to the power of 500 possibilities, it is statistically inevitable that a tiny, tiny fraction of those universes will, purely by chance, have the right combination of constants to allow for stars, planets, and life to emerge. We, quite obviously, must find ourselves in one of those exceptionally rare, life-friendly patches. The hidden pattern is not a single, elegant equation, but a meta-pattern of immense possibility. Our universe is not special, it is simply viable. It is not the product of a cosmic plan, but the outcome of a colossal cosmic lottery where nearly all tickets are losers. But with so many tickets being drawn, a few winning numbers are bound to appear. This landscape picture dovetails perfectly with the theory of eternal inflation we discussed earlier. Imagine the inflating multiverse as a vast, bubbling cosmic foam. Each bubble is a universe undergoing its own Big Bang. The string theory landscape provides the menu for what can happen inside each of those bubbles. When a bubble forms, the extra dimensions within it snap into one of the 10 to the power of 500 possible configurations, randomly selecting a set of physical laws from the landscape. Our universe is just one bubble among an infinite number, one that happened to land on a set of laws that permits our existence. This synthesis offers a powerful, if humbling, resolution to the fine-tuning problem. We are not at the center of a cosmos designed for us. We are a happy accident in a multiverse of overwhelming proportion, a single, conscious blossom in an endless garden of mostly barren and exotic flora. The search for a unique theory of everything may be futile. Instead, we may live in a reality where everything is possible, and our particular corner is just one possible manifestation of a deeper, more diverse mathematical potential. But if the universe permits such a vast landscape of possibilities, does it also contain pathways to our own past? The allure of time travel has captivated the human imagination for centuries, offering the tantalizing possibility of witnessing historical events or correcting personal regrets. And surprisingly, the equations of our most successful theory of gravity, Einstein's general relativity, do not explicitly forbid it. The theory allows for speculative structures like wormholes, theoretical tunnels through spacetime, or paths known as closed time-like curves, which could, in principle, allow an object to loop back into its own past. This mathematical permissibility suggests a cosmos where history might be an open book, waiting to be rewritten. Yet, the universe appears to have a powerful safeguard against such temporal tampering, a hidden pattern of cosmic consistency championed by Stephen Hawking. He called this the chronology protection conjecture, a proposed principle of physics that essentially says the universe will not allow you to change the past, because it has a vested interest in protecting the logical sequence of cause and effect. To understand why time travel is even a theoretical possibility, we need to look at the flexibility of spacetime itself. General relativity describes gravity not as a force, but as the curvature of the four-dimensional fabric of the universe by mass and energy. This fabric is not rigid. It can be warped, twisted, and even torn in theory. One of the most famous hypothetical structures is the wormhole, often visualized as a shortcut connecting two distant points in space, or even two different moments in time. If one end of a wormhole were accelerated to near light speed and then brought back, time dilation effects from special relativity would cause that end to age more slowly than the stationary end. The two mouths of the wormhole would then be out of sync, with one existing in the past relative to the other. Walking through it would be a journey across both space and time. Similarly, the intense gravitational field near a rapidly rotating massive object, like a theoretical infinitely long cylinder, could twist spacetime so severely that it forms a closed time-like curve, a path through spacetime that loops back on itself, allowing a traveler to return to their own starting point in both space and time. These are not just flights of fancy. They are valid, albeit highly exotic, solutions to Einstein's field equations. However, the fact that something is mathematically possible does not mean it is physically achievable. This is where Hawking's profound insight comes into play. He noticed that whenever a situation arises that could create a time machine, something always seems to go wrong. Quantum mechanics, the rules governing the very small, appears to step in and prevent the paradoxes before they can occur. Hawking famously quipped that the absence of tourists from the future is perhaps the strongest evidence that time travel to the past is impossible. But his conjecture is far more sophisticated than a simple one-liner. He proposed that the universe possesses a form of chronology protection, a self-correcting mechanism that prevents closed time-like curves from forming. The hidden pattern is not a physical barrier, but a law of logical consistency woven into the quantum fabric of reality. The mechanism for this protection is believed to be a runaway quantum effect. Imagine trying to stabilize a wormhole to make it traversable. To do this, you would need a form of matter with negative energy density, often called exotic matter, to prop the wormhole's throat open against its natural tendency to collapse. But as soon as you create the conditions for time travel, quantum fields passing through the evolving spacetime would be forced into a feedback loop. Virtual particles which constantly pop in and out of existence would travel along the closed time-like curve. With each loop, their energy would build up, amplifying itself without limit. This would create an enormous surge of energy that would either destroy the wormhole or warp spacetime so drastically that the time machine could never form in the first place. It's as if the universe has a built-in circuit breaker that trips the moment a temporal paradox threatens to overload the system. The quantum fluctuations that are normally insignificant would become infinitely powerful, ensuring that the timeline remains a single, consistent narrative. This idea of cosmic censorship extends beyond just preventing paradoxes like the infamous grandfather paradox, where a time traveler could prevent their own birth. It speaks to a deeper principle about the nature of reality. History must be self-consistent. The chronology protection conjecture suggests that the universe is fundamentally structured to preserve a coherent story. Events have causes, and those causes have effects in an unbroken chain. Allowing time travel would shatter this foundational logic, creating loops where events could be their own cause, or worse, where contradictions could exist. The hidden pattern, therefore, is one of narrative integrity. The universe seems to insist that the timeline is not a chaotic jumble of editable events, but a stable, linear pattern where each moment is firmly anchored by the moments that came before it. This isn't just a rule. It's a fundamental feature that makes a universe comprehensible and predictable, allowing science and consciousness to exist at all. In protecting chronology, the cosmos is also protecting the very possibility of meaning itself. But what if consciousness itself is not a rare and fragile flame, but a fundamental feature of the cosmos, as basic as mass or electrical charge? This brings us to one of the most profound and speculative frontiers of thought, a place where physics, philosophy, and spirituality converge. This is the idea of cosmic consciousness, a theory that suggests the hidden pattern of the universe is not just mathematical or geometric, but mental, a vast, pervasive field of awareness in which we and everything else participate. To appreciate the radical nature of this proposal, we must first confront the so-called hard problem of consciousness. Neuroscience has made incredible strides in explaining the easy problems, how the brain processes stimuli, integrates information, and controls behavior. We can map which neurons fire when you see the color red or feel pain. But none of these biological explanations answer the fundamental question: why do we have any inner experience at all? Why is there a subjective, what it is like to be you? A feeling of redness or a sensation of pain, accompanying those neural processes? This qualitative, first-person experience is the mystery. It seems that you could describe all the physical workings of a brain in perfect detail, and still have no account of why consciousness emerges. This has led some thinkers to propose that consciousness might not emerge from complex computation at all. Instead, it might be a fundamental property of the universe, present in some form everywhere. This view is known as panpsychism, from the Greek words pan meaning all and psyche meaning soul or mind. Panpsychism does not claim that rocks are contemplative or that atoms are depressed. That is a caricature. Rather, it proposes that consciousness, or at least a primitive form of it, what we might call proto-consciousness, is a ubiquitous and fundamental aspect of reality. Just as elementary particles have properties like mass and spin, they might also possess an extremely basic form of subjective experience. An electron's inner world would be unimaginably simple, perhaps just a faint hum of existence, a single point of raw feeling. But when these particles combine into increasingly complex systems, like a human brain with its trillions of interconnected neurons, these micro-level conscious experiences could combine and unify to produce the rich, complex consciousness we enjoy. In this view, consciousness didn't magically appear at some point in evolutionary history. It was always there, and life simply found a way to amplify and organize it. How could this possibly work? One compelling analogy is to think of consciousness as a fundamental field, much like the gravitational or electromagnetic fields that permeate the cosmos. We don't think of the gravitational field as emerging from matter. It is a basic feature of space-time that interacts with matter. Similarly, a field of proto-consciousness could be a fundamental component of the universe. Matter, then, wouldn't produce consciousness through some mysterious alchemy. Instead, matter would be inseparable from consciousness. The two would be different aspects of the same underlying reality. The physicist and mathematician Roger Penrose, along with anesthesiologist Stuart Hameroff, have proposed a specific version of this idea, suggesting that consciousness arises from quantum vibrations within the microtubules of brain cells. While their theory is highly controversial, it points toward a deeper integration of mind and cosmos, where quantum processes, which are fundamental to all matter, play a direct role in generating subjective experience. The implications of cosmic consciousness are staggering. It would mean that the universe is not a vast, unconscious machine, but a living, experiencing entity. Our own consciousness would not be a fluke inside a dead universe, but a localized expression of a universal mind. This perspective offers a new answer to the ancient philosophical question of why the universe is mathematically intelligible. Perhaps the reason our minds can comprehend the cosmos is because both are rooted in the same fundamental ground of consciousness. The laws of physics would not be arbitrary rules imposed on an inert substance, but the inherent habits of a cosmic mind thinking itself into existence. This idea resonates with philosophical traditions from idealism to certain interpretations of quantum mechanics, where the act of observation seems to play a crucial role in defining reality. It suggests that the ultimate hidden pattern is one of self-awareness, a universe that is not merely known, but is itself a process of knowing. While the chronology protection conjecture guards against paradoxes in time, our own motion through space presents a different kind of puzzle, one that points to a colossal and unseen presence in our cosmic backyard. After contemplating the universe's fundamental rules, we return to the realm of direct observation to confront a gravitational mystery that has tugged at our galaxy for billions of years. This is the enigma of the Great Attractor, a vast and hidden concentration of mass that is pulling us, and countless other galaxies, toward a specific point in the void, revealing a hidden pattern of motion on the grandest of scales. Our story begins not with a telescope's direct image, but with a careful mapping of cosmic velocities. For decades, astronomers have known that our Milky Way galaxy is not sitting still. It is moving at an incredible speed of over 2 million kilometers per hour relative to the afterglow of the Big Bang. For a long time, this motion was largely attributed to the gravitational pull of a nearby, massive cluster of galaxies known as the Virgo cluster. But as measurements became more precise in the 1970s and 80s, it became clear that the Virgo cluster's pull was only part of the story. There was an additional, even more powerful force at work. Our entire local group of galaxies, including Andromeda and the Milky Way, was being drawn towards something far more distant and immensely more massive, lying in the general direction of the constellations Centaurus and Hydra. This mysterious source of gravity was dubbed the Great Attractor. The true nature of this cosmic lure, however, is frustratingly difficult to study because of its location. It lies almost directly behind the crowded, dusty, and gas-filled plain of our own Milky Way, a region astronomers call the zone of avoidance. From our vantage point on Earth, trying to see the Great Attractor is like trying to spot a distant mountain range through the thick fog and bright lights of a sprawling city. The visible light from galaxies in that direction is completely absorbed or scattered by the intervening material of our galaxy's disk. For a long time, this zone was a literal blind spot in our maps of the universe. But scientists are resourceful. They turn to instruments that can see through the cosmic fog, using radio, infrared, and X-ray telescopes to peer past the dust and gas. What these observations have revealed is astonishing. The Great Attractor is not a single, unimaginably dense object, but rather the central gravitational heart of a sprawling supercluster of galaxies, now known as the Laniakea supercluster, a Hawaiian word meaning immense heaven. Laniakea is breathtaking in its scale. It is a vast cosmic watershed, a web of filamentary structures containing over 100,000 galaxies, all flowing inward toward the Great Attractor's gravitational basin, much like rivers flow toward the ocean. Our own Milky Way is just one small town on the outskirts of this immense metropolitan area of the cosmos. The mass required to generate such a powerful gravitational pull is staggering, equivalent to tens of thousands of Milky Way galaxies. This is the core of the mystery. According to the standard model of cosmology and the principle that the universe should be homogeneous on the largest scales, such an enormous concentration of mass in one region should not exist. The Great Attractor represents a significant lumpiness, a deviation from the expected smooth distribution of matter that challenges our understanding of how structure forms. It suggests that dark matter, the invisible scaffolding of the cosmos, may be clumped in ways our models have not fully predicted, creating gravitational anchors far more powerful than we anticipated. Yet, the story deepens even further. Recent observations indicate that the Great Attractor itself may not be the final destination in our cosmic journey. The entire Laniakea supercluster, including the Great Attractor, appears to be part of an even larger river of galaxies, all flowing toward an impossibly vast and distant structure known as the Shapley supercluster, the largest known concentration of mass in the observable universe. This reveals a hidden pattern of nested cosmic currents, where galaxies move within groups, groups within clusters, clusters within superclusters, and superclusters within these immense flows, all dictated by the gravitational landscape shaped by both visible and dark matter. The Great Attractor is not an anomaly in isolation. It is a major landmark in a cosmic geography we are only beginning to chart. Its persistent pull reminds us that our place in the universe is dynamic, that we are part of a grand gravitational dance whose full choreography is still being uncovered, hinting at structures of unimaginable size whose gravity shapes the fate of everything we can see. After journeying through these 30 astonishing theories, from the mathematical underpinnings of reality to the holographic projections and the branching multiverses, we are left with one final, humbling question. Is it possible that all these hidden patterns, these diverse and sometimes contradictory maps of reality, are themselves just different facets of a single, ultimate pattern? This is the dream that has driven physics for over a century, the quest for a theory of everything, a final, elegant framework from which the entire cosmos, in all its bewildering complexity, would effortlessly emerge. Imagine finding a master key that could unlock every door in an endless mansion. A theory of everything would be that key for the universe. It wouldn't just unify general relativity and quantum mechanics. It would be a single principle from which space, time, matter, and the very forces of nature would crystallize as natural consequences. The allure of this idea is immense. It speaks to a deep-seated human belief that beneath the apparent chaos of existence lies a fundamental order, a beautiful and simple truth. We see echoes of this desire in every era, from the ancient Greeks who believed the cosmos was built from perfect geometric solids, to Einstein spending his later years searching for a unified field theory. It is the hope that the universe is not just a collection of ad hoc rules, but a coherent, intelligible whole. The success of earlier unifications fuels this optimism. James Clerk Maxwell unified electricity and magnetism into a single electromagnetic force. Later, the electromagnetic force was unified with the weak nuclear force into the electroweak force. The pattern suggests a progression toward a final, grand synthesis, a theory so powerful it would feel less like a human invention and more like a discovery of the universe's original blueprint. Yet, as we stand on the precipice of this dream, we must confront two starkly different possibilities for what such a final theory would actually reveal. The first is a vision of breathtaking simplicity. Perhaps the core of reality is a single, elegant equation, something as fundamentally simple and beautiful as E equals mc squared, but with consequences that blossom into all of physics. This would be the ultimate hidden pattern, a seed of pure mathematical logic from which the entire tree of existence grows. In this view, the apparent complexity of the world, the countless particles, the forces, the constants, would be an illusion, much like the intricate patterns of a snowflake are all generated by the simple, repetitive rules of crystal formation. The universe's diversity would be a magnificent expression of an underlying unity, a cosmic symphony played from a minimal set of notes. This is the promise of theories like string theory or loop quantum gravity at their most ambitious, the hope that we will one day peer past the curtain and find not more machinery, but a statement of stunning, economical beauty. The second possibility is far more unsettling and in some ways more profound. What if the universe's complexity is not an illusion, but fundamental? What if there is no single, simple pattern at the bottom? The landscape of string theory, with its 10 to the power of 500 possible universes, hints at this. A final theory might not be a unique equation, but a vast menu of possibilities, a cosmic lottery where our universe is just one winning ticket. In this scenario, the quest for a single elegant pattern would be misguided. The ultimate law might not be a beautiful equation, but a principle of proliferation, a rule that generates endless diversity. The hidden pattern would be that there is no single hidden pattern, only a meta-pattern of potentiality. This wouldn't be a failure of science. It would be a monumental discovery about the nature of existence. It would tell us that the universe is inherently creative, an engine for generating novelty rather than a clockwork mechanism following a predetermined script. The richness we see would not be reducible to something simpler. It would be the primary feature of reality. This brings us to the heart of the matter, the human drive that has propelled this entire exploration. Our search for hidden patterns is more than a scientific endeavor. It is a fundamental part of what it means to be conscious in a vast and mysterious cosmos. From our earliest ancestors charting the stars to modern physicists colliding particles, we have been driven by a need to find order, to make sense of our place in the grand scheme of things. This quest for understanding is a story of incredible audacity. Here we are, on a tiny planet orbiting an average star, using our 3-pound brains to attempt to decode the logic of the entire universe. The very fact that we can make progress, that mathematics we invent in our minds can accurately describe the behavior of galaxies and quarks, is itself a miracle that demands an explanation. Perhaps it is evidence of a deep kinship between our consciousness and the cosmos, a hint that we are not separate observers but active participants in a universe that is, in some sense, waking up to itself through us. So, will we ever find a final theory? The answer may be less important than the search itself. The journey to uncover the universe's hidden patterns has already transformed our world, giving us technologies and insights that have reshaped civilization. More importantly, it has expanded our imagination and deepened our sense of wonder. Each new theory, whether it ultimately proves correct or not, is a testament to our boundless curiosity. They are not just answers to puzzles. They are new ways of seeing, new lenses through which to perceive the sublime architecture of reality. The pattern we ultimately discover may be one of elegant simplicity or irreducible richness. But perhaps the most beautiful pattern of all is the enduring human spirit of inquiry, the relentless drive to look into the darkness and ask, what lies beyond? This dialogue with the cosmos, this eternal quest for meaning, is the most profound connection we have with the universe, a pattern of curiosity woven into the very fabric of our being. So, where does this leave us? We have ventured across an incredible landscape of ideas, from the mathematical universe hypothesis, which suggests reality is a grand computation, to the holographic principle that reimagines our cosmos as a two-dimensional projection. We have wrestled with the eerie connections of quantum entanglement and contemplated the cosmic censorship that may protect the flow of time itself. We have seen the universe as a fractal, a symphony, a cyclic phoenix, and even a sophisticated simulation. The sheer diversity of these theories is staggering, yet they are all united by a single, powerful conviction: that the universe is not random chaos, but a reality woven with deep, intricate patterns waiting for us to discover. The true wonder, perhaps, is not just that these patterns exist, but that we are here to perceive them. We are a species born from stardust, living on a tiny rock orbiting an average star, and yet we can formulate equations that accurately describe the birth of galaxies and ponder the nature of singularities. Our consciousness allows us to look up at the night sky and not only see points of light but to ask why. This relentless curiosity is, in itself, one of the most profound patterns in the cosmos. It is the driving force that has taken us from ancient myths to quantum field theory, a thread of inquiry that connects every human who has ever wondered about their place in the grand scheme of things. The universe may be built on mathematics, or it may be a vast simulation, but its greatest marvel could be that it has evolved creatures capable of trying to read its source code. This journey does not end with a definitive answer because the nature of exploration is to constantly push the boundaries of the known. Each theory we have explored is a map, and like all maps, they are simplifications of a territory far more complex and mysterious than we can imagine. Some of these maps will be refined by future discoveries, others may be discarded entirely, but each one represents a courageous leap of the human imagination, an attempt to impose order on the sublime chaos of existence. They remind us that science is not a collection of facts, but a living, breathing process of questioning, doubting, and dreaming. The value is in the quest itself, in the expansion of what we believe is possible. Now, we turn the question over to you. After this journey to the edge of understanding, which of these theories resonates most deeply? Does the elegant simplicity of the principle of least action feel like a fundamental truth? Or does the boundless possibility of the many worlds interpretation capture your imagination? Perhaps the biological wisdom of the Gaia hypothesis or the cosmic connectivity of quantum entanglement speaks to your view of reality. The conversation is far from over, and your perspective is a vital part of it. Share your thoughts in the comments below. We are genuinely curious to hear which cosmic puzzle captivates you the most. And if your mind is reeling from these ideas and you are hungry for more journeys into the unknown, consider subscribing to the channel. There are always more mysteries to explore, more patterns to uncover, and we are just getting